4.37 light-years. That is the distance to Alpha Centauri, our nearest stellar neighbour. In cosmic terms, this is nothing, a mere stone's throw across the vast ocean of space. Yet this distance represents an insurmountable barrier that may forever separate humanity from the stars. We dream of interstellar travel. Science fiction has conditioned us to believe it is inevitable. Starships gliding between solar systems, colonies on distant worlds, first contact with alien civilizations. These images fill our collective imagination. But reality tells a different story. A story written in the unforgiving mathematics of physics, energy, and time. Alpha Centauri is actually a triple star system. Alpha Centauri A and B orbit each other closely, while Proxima Centauri, a small red dwarf, circles them both at a vast distance. Proxima hosts at least 2 confirmed planets, including Proxima b, a rocky world in the habitable zone. This makes it the closest potentially habitable exoplanet we know of. Tantalizing, unreachable. The fastest spacecraft humans have ever built is the Parker Solar Probe. It reached speeds of 430,000 miles per hour while diving close to the Sunday. At that velocity, reaching Alpha Centauri would take 6,300 years. Not generations, not centuries, millennia. By the time any probe we launched today arrived, human civilization as we know it might not exist. Languages would have evolved beyond recognition. Nations would have risen and fallen. The very reasons for launching the mission would be forgotten. This is not pessimism. This is physics. The speed of light imposes absolute limits on how fast anything with mass can travel. Chemical rockets, the technology that took us to the moon, are pathetically inadequate for interstellar distances. Nuclear propulsion, often proposed as the solution, faces equally daunting obstacles. Fusion drives, antimatter engines, laser sails, each promising technology collapses under scrutiny when applied to a journey measured in light-years. Energy requirements alone are staggering. To accelerate even a small probe to 10% of light speed requires energy equivalent to thousands of nuclear weapons. To then decelerate at the destination requires the same again. No power source we possess can generate such quantities. No fuel we can imagine would fit aboard a spacecraft and still leave room for payload. But energy is just one problem. Radiation bombardment from cosmic rays would destroy electronics and biological tissue over decades of flight. Micrometeorites travelling at relative velocities of thousands of kilometers per second would shred any hull we could build. Communication delays of 4 years each way would make real-time mission control impossible. Life support systems would need to function perfectly for centuries. Navigation errors of fractions of degrees would miss the target by light years. And perhaps most troubling, we have no way to slow down once we arrive. The night sky makes Alpha Centauri look close. 3 dim stars forming a tight triangle in the southern constellation Centaurus. Through binoculars, they appear as pinpricks of light, indistinguishable from thousands of others. But those pinpricks represent distances that mock every achievement of human engineering. We have sent probes to every planet in our solar system. We have landed robots on Mars and Titan. We have photographed Pluto and the edge of the heliosphere. Yet all of these accomplishments combined represent less than 1/10,000th of the distance to Alpha Centauri. If you truly want to understand why interstellar travel remains beyond our reach, you need to confront the brutal realities of physics, engineering, and energy. You need to examine each proposed solution and watch it fail against the mathematics of deep space. The answers are not comforting, they are not hopeful, but they are honest, and they reveal something profound about our place in the cosmos. The tyranny of distance. Alpha Centauri lies 4.37 light-years from Earth. This number sounds manageable until you convert it to familiar units. 4.37 light-years equals 41.3 trillion kilometers, or 25.7 trillion miles. Written out, that is 41 trillion, 300 billion kilometers. The human mind cannot grasp such distances through intuition alone. We need comparisons, analogies, calculations that ground the abstract in concrete terms. The Moon sits 384,400 kilometers from Earth. Apollo 11 covered that distance in 3 days using chemical rockets. If we could travel to Alpha Centauri at the same speed Apollo traveled to the Moon, the journey would take 870,000 years. That is 4 times longer than Homo sapiens has existed as a species. The pyramids would be built and crumble to dust 300 times over during such a voyage. But we can do better than Apollo, right? The Voyager 1 probe, launched in 1977, is humanity's most distant ambassador. It travels at 61,000 kilometers per hour relative to the Sunday. This is 17 kilometers per second faster than any previous deep space mission. At Voyager's speed, reaching Alpha Centauri would still require 73,000 years, 73 millennia. That is longer than human civilization has existed, longer than we have had written language, agriculture, or permanent settlements. The New Horizons spacecraft, which flew past Pluto in 2015, travels even faster, 58,500 kilometers per hour. Its journey to Alpha Centauri would take roughly 78,000 years. The Parker Solar Probe, our current speed champion, reaches 430,000 miles per hour during close solar passes. Convert that to kilometers, 692,000 kilometers per hour. Even at this blistering pace, the fastest a human-made object has ever traveled, Alpha Centauri remains 6,300 years away. 6,300 years. That takes us back to before the Bronze Age, before the wheel, before the first cities rose in Mesopotamia. These are not theoretical limitations. These speeds represent the absolute maximum we have achieved after 70 years of spaceflight. We are not talking about future technologies or optimistic projections. These are the fastest velocities we have actually reached, using every available resource and decades of accumulated expertise. And they are pathetically, laughably inadequate for interstellar travel. Consider what happens during these timescales. A 6,300-year mission means that 250 generations would live and die during the voyage. The crew that arrives would be as distant from the crew that departed as we are from the ancient Sumerians. Languages would evolve, cultures would transform, the original mission objectives would be forgotten, reinterpreted, or abandoned. The society that launched the mission would no longer exist in any recognizable form. Even if we could build a ship that lasted 6,300 years, and we cannot, who would maintain it? Who would repair systems when they fail, as they inevitably would? Who would preserve the knowledge needed to operate the vessel? Who would remember why they were going and what they hoped to find? Generational ships appear often in science fiction, but they ignore the brutal reality of institutional continuity. Civilizations rise and fall in less time than such a voyage would require. The distance problem compounds at every scale. Our fastest probes would take human lifetimes just to travel 1 light month. 1 light year requires centuries. 4 light years demands millennia. And Alpha Centauri, despite being our nearest stellar neighbour, is still unreachably far. If we treat the distance from Earth to the Sun as 1 centimetre on a scale model, Alpha Centauri would sit 271 metres away. Our fastest spacecraft would crawl across that distance at a pace of 4 millimeters per year. Even if we achieved 10% of light speed, a velocity requiring revolutionary breakthroughs, we will examine later, the journey would still take 43 years. That is one human lifetime. Barely fast enough for a person to depart as a young adult and arrive at retirement age. And 10% light speed is not a modest goal. It represents a 100-fold improvement over our current capabilities. A leap more significant than the gap between the first aeroplane and the space shuttle. The Breakthrough Starshot initiative, proposed by physicist Stephen Hawking and investor Yuri Milner in 2016, aims for exactly this: 20% light speed. Their concept uses laser propulsion to accelerate tiny probes to relativistic velocities. Even if successful, and the technical challenges are immense, these probes would take 20 years to reach Alpha Centauri. Add 4 years for the signal to return, and you are looking at a 24-year round trip for information. No human payload, no return capability. Just data transmitted across the void. This is the fundamental constraint that makes interstellar travel so difficult. Distance itself becomes an enemy. Not because space is hostile, though it is, but because traversing it requires time, and time erodes everything. It degrades materials, exhausts resources, strains human psychology, and transforms societies beyond recognition. The tyranny of distance is not merely a technical problem to be solved. It is a fundamental feature of the universe we inhabit, one that may forever confine humanity to its birthplace, gazing at neighbouring stars we can never touch. The energy problem. Accelerating any mass to high velocities requires energy, enormous amounts of energy. The kinetic energy equation, 1/2 mass times velocity squared, reveals why interstellar travel is so difficult. The energy needed grows with the square of velocity. Doubling your speed requires 4 times the energy. Tripling it needs 9 times. Reaching 10% of light speed requires 100 times more energy than reaching 1%. Let us start with concrete numbers. A small interstellar probe, say 1 kilogram travelling at 10% light speed, possesses kinetic energy of approximately 450 trillion joules. That equals the explosive yield of 108 tons of TNT. To accelerate our 1 kilogram probe requires the energy equivalent of 2 Hiroshima bombs, and that is just to reach cruising speed. Deceleration at the destination requires the same energy again, so our minimal payload needs 216 tons of TNT equivalent just for velocity changes. Now consider a realistic probe. The New Horizons spacecraft, which visited Pluto, weighed 478 kilograms. Scale up our calculation. Accelerating New Horizons to 10% light speed would require 215,000 terajoules of energy. That is roughly 51 megatons of TNT. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, yielded 50 megatons. So launching a Pluto-sized probe to Alpha Centauri would require detonating the most powerful nuclear device in history just to reach cruising speed. Then detonating it again to slow down. These numbers assume perfect efficiency, that every joule of input energy becomes kinetic energy of the spacecraft. Real rockets are nowhere near perfectly efficient. Chemical rockets, the workhorses of spaceflight, convert only about 65% of their fuel's energy into kinetic energy. The rest becomes heat, light, and exhaust velocity, exceeding what is needed. Even the most optimistic nuclear propulsion concepts struggle to exceed 80% efficiency. Factor in realistic efficiency, and our energy requirements increase proportionally. The rocket equation derived by Konstantin Tsiolkovsky in 1897 adds another layer of difficulty. Any rocket must carry its fuel with it. But fuel has mass, which means you need more fuel to accelerate the fuel, which adds more mass, which requires more fuel. This recursive problem means that the mass ratio, the ratio of fueled mass to empty mass, grows exponentially with the desired velocity change. For chemical rockets, this becomes prohibitive almost immediately. The Space Shuttle's external tank and solid rocket boosters contained roughly 2,000 tons of propellant to accelerate 110 tons of shuttle and payload. That is a mass ratio of about 20 to 1, and the shuttle barely reached orbital velocity of 8 kilometers per second. To reach 10% light speed, 30,000 kilometers per second, using chemical rockets would require a mass ratio so extreme that the spacecraft would be microscopic compared to its fuel tank. Let us calculate this precisely. Using the rocket equation with hydrogen-oxygen propulsion, exhaust velocity of 4.5 kilometers per second, and targeting 10% light speed, 30,000 kilometers per second, the mass ratio comes out to approximately E 30,045, which equals E 6,667. This number is so large, it is meaningless. It means that for every kilogram of payload, you would need 10,2,894 kilograms of fuel. For comparison, the observable universe contains approximately 1053 kilograms of matter. Our rocket would require fuel masses exceeding the total mass-energy content of trillions upon trillions of universes. Chemical propulsion is clearly impossible for interstellar missions. What about nuclear power? Nuclear fission releases about 1 million times more energy per kilogram than chemical reactions. Nuclear fusion releases even more, about 4 times as much as fission for hydrogen fusion into helium. These represent dramatic improvements, but even nuclear propulsion faces severe limitations. The most studied nuclear rocket concept is the nuclear thermal rocket. This design heats propellant, typically hydrogen, using a nuclear reactor, then expels it through a nozzle. Exhaust velocities reach 8 to 9 kilometers per second, roughly twice that of chemical rockets. This cuts the mass ratio substantially. But for 10% light speed, the ratio still comes to approximately E 30,009, or E 3,333. Still impossible. Still requiring more fuel than exists in the universe. Nuclear Pulse Propulsion Project Orion, studied in the 1,960 seconds, offers better performance. This concept involves detonating nuclear bombs behind a massive pusher plate, using the explosion's momentum to accelerate the spacecraft. Exhaust velocities could theoretically reach 10,000 kilometers per second for high-yield fusion devices. The mass ratio becomes E 30,010,000, or E 3, roughly 20 to 1. This is actually achievable. But it means that 95% of your launch mass is nuclear weapons. And you need thousands of them for the acceleration phase, then thousands more for deceleration. The logistical problems are staggering. Manufacturing thousands of nuclear devices requires enriched uranium or plutonium. Lifting them to space requires massive launch infrastructure. Assembling them into a spacecraft means handling nuclear materials in orbit, and then detonating them in sequence during acceleration, hoping none fail, none detonate prematurely, and none damage the pusher plate beyond repair. Project Orion, studies in the 1,960 seconds, concluded this might be technically feasible, but politically and economically impossible. Fusion rockets represent another option. If we could build a rocket that continuously fuses hydrogen into helium, essentially a controlled thermonuclear reactor as an engine, exhaust velocities could reach 30,000 kilometers per second or more. At that performance, a fusion rocket could reach 10% light speed with a mass ratio of less than 3:1. Suddenly, interstellar travel becomes plausible from an energy standpoint. But here is the problem. We cannot build fusion rockets. We have not even built a fusion reactor that produces net energy gain in a laboratory, let alone one compact enough and robust enough to mount on a spacecraft. The ITER project in France, the world's largest fusion experiment, aims to achieve sustained fusion by 2035. Even if successful, ITER will be a massive facility requiring enormous infrastructure. Miniaturizing this to spacecraft scale represents a challenge of unknown difficulty that may take decades or centuries to solve, if it is even possible. Antimatter offers theoretical advantages. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy, according to Einstein's equation, E equals mc squared. This is the ultimate energy density, nothing can surpass it. A matter-antimatter rocket could achieve exhaust velocities approaching light speed, making 10% cruising velocity achievable with modest mass ratios. The problem? We cannot make antimatter in meaningful quantities. Particle accelerators, like the Large Hadron Collider, produce tiny amounts nanograms per year. Creating 1 gram of antimatter would require the total electrical output of the United States running for 1 year and cost approximately $25 trillion. An interstellar mission might need tons of antimatter. The energy and economic costs are so far beyond current capabilities that antimatter propulsion remains pure speculation. Even if we solved the antimatter production problem, storage presents another challenge. Antimatter cannot touch normal matter without annihilating. It must be confined using electromagnetic fields in ultra-high vacuum. Any containment failure means instant detonation. Storing tons of antimatter safely for decades or centuries during an interstellar voyage seems impossible with any technology we can envision. The radiation barrier. Space is not empty, it is filled with radiation. High-energy particles stream constantly from the sun, the solar wind. Cosmic rays from distant supernovae and active galactic nuclei bombard everything. These particles move at relativistic speeds, carrying enough energy to damage both electronics and biological tissue. On Earth, we are protected by 2 shields, our atmosphere and our magnetic field. Both absorb or deflect radiation before it reaches the surface. In deep space, there is no protection. The solar wind consists primarily of electrons and protons ejected from the sun at speeds of 400 to 800 kilometers per second. Within the solar system, this creates a relatively benign radiation environment. Spacecraft like Voyager must handle solar wind exposure, but it is manageable. Beyond the heliosphere, the bubble of solar influence, extending roughly 120 astronomical units from the sun, the solar wind disappears. But it is replaced by something worse, unshielded cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, traveling at near light speed. They originate from supernova explosions, neutron stars, and other violent cosmic events. When these particles strike matter, they create secondary particles through nuclear reactions. This cascade of particles can penetrate deep into materials, damaging molecular structures and genetic information. Measurements from the Voyager probes, now in interstellar space, show cosmic ray intensities about twice as high as within the heliosphere. An astronaut in interstellar space would receive a radiation dose of approximately 0.2 to 0.4 gray per year from galactic cosmic rays alone. For comparison, the lethal dose for humans is about 5 Gray received over a short period, so cosmic rays will not immediately kill you. But chronic exposure over years or decades causes cumulative damage, increased cancer risk, cataracts, cardiovascular disease, and central nervous system effects. For electronic systems, radiation causes different problems. High-energy particles can flip bits in computer memory, so-called single-event upsets. They can cause permanent damage to semiconductor devices. They can degrade solar panels and sensors. Spacecraft operating within the solar system face these issues and mitigate them through radiation-hardened components and redundant systems. But an interstellar mission lasting decades or centuries faces accumulated radiation damage that will eventually destroy unhardened electronics. Shielding helps, but comes at enormous cost. The most effective shielding is mass, thick layers of material that absorb radiation before it reaches sensitive components or crew. Water is particularly good. Hydrogen nuclei in water molecules effectively scatter incoming protons. Studies suggest that 2 meters of water shielding would reduce cosmic ray exposure by roughly 50%. But 2 meters of water surrounding a spacecraft adds hundreds of tons of mass, dramatically increasing fuel requirements. Alternative shielding concepts include magnetic fields. Earth's magnetosphere deflects charged particles, suggesting that generating an artificial magnetic field around a spacecraft could provide protection. But the energy requirements are prohibitive. Creating a magnetic field strong enough and extensive enough to shield a spacecraft requires superconducting magnets and continuous power input. The mass of the magnets, power supply, and cooling systems would likely exceed that of passive shielding. Active shielding using electrostatic or electromagnetic fields to deflect particles faces similar challenges. Proposals exist, but none have been demonstrated at scale, and all require power, adding more mass for reactors or solar panels. Mass is the enemy of interstellar travel. Every kilogram of shielding increases fuel requirements substantially. The radiation problem worsens at high velocities. As a spacecraft approaches relativistic speeds, even the thin interstellar medium becomes dangerous. At 10% light speed, hydrogen atoms, which float sparsely through space at a density of about 1 per cubic centimeter, strike the spacecraft with energies equivalent to radiation from a nuclear reactor. These collisions erode the hull, create secondary radiation, and heat the spacecraft. At 20% light speed, these effects intensify dramatically. The energy of collision scales with velocity squared. Hydrogen atoms striking the ship at 60,000 kilometers per second carry kinetic energies of about 60 MeV, million electron volts. This is enough to cause nuclear reactions, creating showers of secondary particles. The spacecraft would be flying through what amounts to a particle accelerator beam. Continuous bombardment would erode any material, no matter how strong. Shielding against this requires either incredibly thick armor, hundreds of tons, or some form of active deflection. Magnetic deflection might work for charged particles, but does nothing against neutral atoms. Electrostatic deflection faces the same limitation. Some proposals suggest using a cloud of plasma ahead of the spacecraft to ionize incoming atoms, then deflecting them magnetically. But generating and maintaining such a plasma cloud requires energy and adds complexity. The breakthrough Starshot concept illustrates these challenges starkly. Starshot proposes accelerating gram-scale probes to 20% light speed using ground-based lasers. At that velocity, interstellar hydrogen becomes a severe problem. The probe's thin sail and payload would be sandblasted by relativistic impacts. calculations suggest that erosion and heating could destroy the probe before it reaches Alpha Centauri unless additional shielding is added. But adding shielding to a gram-scale probe defeats the purpose. The probe becomes too heavy to accelerate with feasible laser power. For crewed missions, radiation presents insurmountable obstacles. Human bodies are fragile. DNA damage from cosmic rays accumulates over time, leading to cancer and other diseases. The central nervous system is particularly vulnerable. Studies of mice exposed to cosmic ray analogues show cognitive impairment and memory loss. A crew spending decades in deep space would almost certainly suffer severe health effects, even with the best shielding we could plausibly provide. Medical countermeasures offer little help. Drugs can mitigate some radiation effects, but no pharmaceutical can prevent DNA damage from high-energy particles. Genetic engineering might increase radiation resistance, but this enters speculative territory far beyond current capabilities. The only truly effective countermeasure is shielding, lots of it, which brings us back to the mass problem. Even robotic missions face challenges. Electronics must function for decades without maintenance. Radiation gradually degrades semiconductors, introduces errors, and eventually causes failures. Redundant systems help, but redundancy adds mass and complexity. Eventually, accumulated damage exceeds the system's ability to compensate. The spacecraft fails. Some propose that future nanotechnology or quantum computers might resist radiation better than current electronics. Perhaps, but we have no way to build such systems today, and even theoretical proposals face limits. At some point, sufficient radiation damage will destroy any information processing system, no matter how cleverly designed. The communication gap. Imagine launching a probe to Alpha Centauri. Decades or centuries pass. Finally, it approaches the target system. Instruments begin collecting data, spectroscopy of the stars, images of potential planets, measurements of radiation environments. All useless unless that data can return to Earth. And here we encounter another fundamental barrier: communication across interstellar distances. Radio waves travel at light speed. This is the fastest possible transmission rate set by physics itself. From Alpha Centauri, any signal requires 4.37 years to reach Earth. Ask the probe a question. Wait 4.37 years for the signal to arrive. Wait while the probe processes your query, then wait another 4.37 years for the response. Total round-trip communication time, 8.7 years. This delay makes real-time control impossible. If the probe encounters a problem, a navigation error, a system failure, an unexpected obstacle, ground controllers cannot help. By the time the warning signal reaches Earth and a response returns, nearly 9 years have passed. The probe must handle every situation autonomously. There are no do-overs, no tech support, no emergency repairs from mission control. The probe must be intelligent enough to make every decision independently. It must troubleshoot its own failures, adapt to unexpected conditions, and prioritize which data to collect and transmit. This requires artificial intelligence far more sophisticated than anything we have built. Current AI systems excel at narrow tasks but struggle with open-ended problem-solving. Building an AI that can manage an interstellar mission autonomously for decades is a challenge we have barely begun to address. But even assuming perfect autonomy, the communication problem remains. Transmitting data across light years is extraordinarily difficult. Signal strength decreases with the square of distance. Double the distance, and you need 4 times the power to maintain the same signal strength at the receiver. Alpha Centauri is roughly 270,000 times farther from Earth than the Sunday. Signal strength drops by a factor of 270,000 squared or 73 billion times weaker. Current deep space missions, like Voyager, demonstrate this challenge. Voyager 1, now about 24 billion kilometers from Earth, transmits with a 23-watt transmitter. That is roughly the power of a refrigerator light bulb. By the time the signal reaches Earth, it has weakened to about 10-16 watts. We can still detect it using massive 70-meter radio dishes and extremely sensitive receivers. But data rates are glacial 160 bits per second. Sending a single smartphone photo would take hours. Alpha Centauri is 1,700 times farther than Voyager's current distance. Signal strength would drop by 1,700 squared, or 3 million times weaker than Voyager. Even with a more powerful transmitter and better receivers, data rates would be measured in bits per day, not bits per second. Transmitting a single high-resolution image could take months. Sending gigabytes of scientific data could require centuries. Increasing transmitter power helps, but only linearly. A 230-watt transmitter, instead of 23 watts, improves things by a factor of 10. But power comes from somewhere. Solar panels do not work in deep space. Sunlight is too weak beyond the solar system. Radioisotope thermoelectric generators, RTGs, which convert heat from radioactive decay into electricity, provide power for decades, but at limited output. Voyager's RTGs originally produced 470 watts. After more than 4 decades, they now produce about 250 watts and decline by about 4 watts per year. An interstellar probe would need power for decades or centuries. RTGs based on plutonium-238 decay too quickly. The half-life is 88 years. Other isotopes last longer, but produce less power per kilogram. Nuclear reactors could provide more power, but add mass and complexity. And all of this assumes we can keep the transmitter pointed at Earth with extraordinary precision across light years while the spacecraft tumbles or maneuvers. Pointing accuracy becomes critical. Radio signals spread out as they travel, but directional antennas can focus them into narrow beams. A highly directional antenna might concentrate the signal into a cone just 1 degree wide, but across 4 light years, 1 degree of uncertainty means the beam might miss Earth entirely. The probe must know its position and orientation with incredible precision and maintain that accuracy for decades, despite vibrations from maneuvering, thermal expansion from solar heating, and gradual drift from gyroscopic effects. Error correction adds overhead. All communication channels have noise, random interference that corrupts data. Distant, weak signals have terrible signal-to-noise ratios. To ensure accurate data reception, you must add redundancy, error-correcting codes that allow the receiver to detect and fix corrupted bits. But error correction is not free. It reduces effective data rates. A channel that nominally supports 1 bit per second might only transmit 1 useful bit per 100 seconds after error correction overhead. Optical communication offers potential improvements. Lasers can be focused into extremely narrow beams, far narrower than radio. This concentrates more power into a smaller area, improving signal strength at the receiver. The Voyager missions use radio, but newer concepts, like Breakthrough Starshot, propose optical communication. A 1-watt laser on the probe, focused to a narrow beam, might be detectable at Alpha Centauri using large, ground-based telescopes. But optical communication introduces new challenges. The probe must point its laser at Earth with even greater precision than required for radio. Pointing errors of microradians millionths of a degree would cause the beam to miss Earth entirely. Achieving this level of pointing accuracy requires star trackers, gyroscopes, and reaction wheels that must function flawlessly for the entire mission. And unlike radio, optical signals are blocked by dust, debris, and planetary atmospheres. If Earth is on the wrong side of the Sun when the probe sends data, the signal is lost. The information rate limit, Shannon's theorem, places fundamental bounds on communication. Even with perfect technology, the amount of information you can transmit depends on signal strength and noise. Across interstellar distances, these limits mean that data rates will be slow no matter what technology we use. You can improve things incrementally, better transmitters, more sensitive receivers, more directional antennas, but the improvements are linear while the challenge is exponential. Consider what this means for an actual mission. A probe reaches Alpha Centauri after decades of flight. It spends months collecting data, mapping planets, analyzing atmospheres, measuring magnetic fields, gigabytes or terabytes of information. Then it begins transmitting. At optimistic data rates, say, 1 kilobit per second transmitting 1 terabyte would take 32 million seconds. That is 1 year of continuous transmission, during which the probe must keep its antenna pointed at Earth, maintain sufficient power, and hope nothing fails. Meanwhile, on Earth, receivers must listen continuously. A single missed reception window could lose irreplaceable data. The signal could be corrupted by interference plasma from the sun, noise from electronics, cosmic ray hits on the receiver. All of this must be filtered, error-corrected, and decoded. And then we wait nearly 4.5 years for the next transmission opportunity. Navigation across the void. Traveling to Alpha Centauri requires knowing where you are going. This sounds trivial. We know where Alpha Centauri is. We can point a telescope at it any time. But knowing the direction to a star and navigating a spacecraft to it across light years are entirely different challenges. The precision required is almost incomprehensible, and the consequences of errors are catastrophic. Alpha Centauri moves through space at approximately 25 kilometers per second relative to the Sunday. During a journey of decades or centuries, the star system will move hundreds of billions of kilometers. We must predict this motion accurately across decades, accounting for its orbital dynamics within the triple star system, gravitational perturbations from nearby stars, and relative motion between the Sun and Alpha Centauri. Any errors in our understanding of stellar motions translate directly into targeting errors. Navigation within the solar system relies on precise tracking from Earth. Ground stations constantly monitor spacecraft positions using radio ranging. We send signals to the spacecraft and measure the round-trip time to determine distance. We measure Doppler shifts to determine velocity. By combining these measurements over time, we calculate trajectories and plan course corrections. This works because communication delays are short minutes to hours, and we can make frequent adjustments. Interstellar navigation is different. Once a probe leaves the solar system, radio signals take years to travel back and forth. You cannot track the spacecraft in real time. By the time you detect a navigation error, the probe has been drifting off course for years. Correcting the error requires a velocity change, which burns fuel you probably do not have. For a lightweight probe pushed by laser, there is no fuel at all. The trajectory you set during the initial acceleration phase is the trajectory you are stuck with forever. Let us calculate acceptable error margins. Suppose we target a flyby distance of 1 astronomical unit, 150 million kilometers from Alpha Centauri A. This gives us a reasonable chance of passing near any planets in the habitable zone. At a distance of 4.37 light-years, this 1 AU target represents an angular precision of about 0.0001 degrees. That is roughly the angular size of a coin viewed from 200 kilometers away. Our initial trajectory must be accurate to this level, or we miss the system entirely. Achieving this precision requires knowing the probe's velocity with extraordinary accuracy. An error of just 1 centimeter per second in the initial velocity, 1/100th of a walking pace, accumulates over 40 years to a position error of 12 million kilometers. That is 30 times the Earth-Moon distance. At 10% light speed, your velocity is 30,000 kilometers per second. You must know this velocity to within 1 part in 3 million, and you must maintain it without course corrections for 4 decades. During flight, many factors perturb the trajectory. Radiation pressure from starlight pushes on the spacecraft, slightly altering its path. The push is tiny, but accumulates over years. The interstellar magnetic field exerts forces on any charged components. Passing through regions of higher or lower gas density creates drag or lift. Each perturbation is small changes of millimeters per second, but over decades they compound into significant errors. The spacecraft must measure its own position and velocity. But how? Within the solar system, we use tracking from Earth. In interstellar space, you are on your own. Star trackers, cameras that photograph star fields and compare them to catalogues, can determine orientation with high precision. But orientation is not position. Knowing which direction you are pointing does not tell you where you are. Measuring position requires triangulation. If you can measure the angles to several stars simultaneously and know their positions precisely, you can calculate your location. But stars are very far away. Even at 10% light speed, 4 years into your journey, you have travelled less than half a light year. The apparent positions of stars barely change. The parallax shifts, the angular changes caused by your motion, are measured in micro-arc seconds. Detecting such tiny angles requires telescopes with extraordinary precision, operating autonomously for decades without calibration or maintenance. Velocity measurement is even harder. You can measure velocity relative to nearby stars using Doppler shifts, measuring how starlight frequency changes due to your motion. But nearby stars are still light years away. Their light is faint. Measuring Doppler shifts to the required precision demands spectrographs with extreme sensitivity and stability. These instruments must function perfectly for the entire mission duration. Accelerometers can measure changes in velocity during acceleration phases, but they drift over time. Errors accumulate. After years of flight, accelerometer data becomes unreliable. You need some external reference to reset your navigation solution periodically. But there is no GPS in interstellar space, no beacons broadcasting position data, no ground stations uploading corrections. You must navigate using only what you can measure directly: starlight, stellar positions, Doppler shifts. Some mission concepts propose sending multiple probes along slightly different trajectories. By comparing their observations and cross-referencing their positions, you can potentially improve navigation accuracy. But this requires communication between probes across thousands or millions of kilometers. It requires synchronized clocks, maintaining accuracy over decades. It multiplies the complexity and cost. Launching several probes instead of one. The rotation of the spacecraft introduces another complication. Even small rotation rates, fractions of a degree per hour, cause instruments to scan across the sky instead of holding steady on targets. This complicates both navigation measurements and science observations. Stabilizing spacecraft rotation requires reaction wheels or control thrusters. Reaction wheels are mechanical devices that eventually wear out. Thrusters consume fuel. Either way, your ability to maintain attitude control degrades over time. Temperature variations cause thermal expansion and contraction of structural components. Over the extreme temperature range of space, from hundreds of degrees above zero when illuminated by stars, to just a few Kelvin in shadow materials, expand and contract by measurable amounts. These dimensional changes alter the optical properties of telescopes and instruments. Calibrations performed during ground testing no longer apply. The spacecraft must recalibrate itself periodically using observations of known stars. But selecting the right stars, measuring them accurately, and adjusting calibrations automatically requires sophisticated software that must function flawlessly for decades. Dust impacts present another navigation hazard. The interstellar medium contains dust grains, tiny particles of carbon, silicates, and ice. At 10% light speed, colliding with a dust grain releases enormous energy. A grain 1 micrometer across about the size of a bacterium carries kinetic energy equivalent to a falling bowling ball. These impacts erode surfaces, pit mirrors, and potentially damage sensitive instruments. Enough impacts could alter the spacecraft's trajectory through momentum transfer. The probe must be designed to withstand this sandblasting for decades while maintaining optical quality sufficient for precision navigation. Consider what happens if navigation fails. Suppose an undetected error causes the probe to miss Alpha Centauri by half a light year, a small error in cosmic terms. The probe flies past, detecting nothing. It transmits data showing empty space. 4 years later, Earth receives the message: mission failure. Decades of effort, billions of dollars, the hopes of a generation all wasted because of a navigation error too small to detect during launch. The survival of systems. Machines fail. This is not pessimism, but engineering reality. Every component has a failure rate. Every system has a finite lifespan. Electronics degrade, moving parts wear out, materials fatigue. We design for redundancy and reliability, but nothing lasts forever. On Earth, when systems fail, we repair them. In Earth orbit, we send astronauts to service satellites. Even on Mars, if a rover breaks, we can diagnose problems and sometimes work around them, but an interstellar probe is different. It must function flawlessly for decades or centuries, with absolutely no possibility of repair, maintenance, or replacement. Consider a simple semiconductor chip, the heart of any electronic system. Cosmic rays striking the chip create permanent damage. Each impact displaces atoms in the silicon crystal lattice, creating defects. Over time, these defects accumulate. Transistors stop functioning, logic gates fail, memory cells become unreliable. We call this total ionizing dose damage, and it is cumulative and irreversible. Radiation-hardened electronics resist this damage better than commercial parts. Military and space-grade components use special fabrication techniques, redundant transistors, and error-correcting memory. The Voyager spacecraft, launched in 1977, still functions today largely because of robust design and radiation-hardened components. But even radiation-hardened parts eventually fail. Voyager is now experiencing component failures after 46 years. An Alpha Centauri mission must last far longer, a century or more, for realistic cruise speeds. We can use redundancy, multiple copies of critical systems, any one of which can fail without ending the mission. Triple redundant computers vote on decisions, with the majority ruling. Redundant sensors provide backup measurements. Redundant transmitters ensure communication survives individual failures, but redundancy adds mass, power consumption, and complexity. And it only delays failure. If you have 3 computers and one fails per decade, you might last 30 years, then you are out of computers. Power systems face similar limits. Radioisotope thermoelectric generators, RTGs, powered the Voyager probes Cassini and New Horizons. RTGs convert heat from radioactive decay into electricity with no moving parts, a robust solution. But the radioactive isotope gradually decays. Voyager's RTGs now produce about half their original power. The thermocouples that convert heat to electricity also degrade from radiation exposure. Eventually, power output drops below minimum mission requirements. For an interstellar mission, we need power for decades or centuries. Plutonium-238, used in most RTGs, has a half-life of 88 years. After 88 years, power drops to 50%. After 176 years, 25%. For a century-long mission, you must design systems to operate on a quarter of initial power, or you carry more plutonium, adding mass that must be accelerated to cruising speed. Alternative isotopes last longer but produce less power per kilogram. Strontium-90 has a 29-year half-life, too short. Americium-241 has a 432-year half-life, but lower power density. The trade-offs are unfavorable. You either accept declining power, add more isotope mass, or explore other power sources. Nuclear reactors could provide more power and longer lifetimes. Reactors can operate for years before requiring refueling, and the fuel can last decades if the reactor runs at low power. But reactors are complex. They have pumps, heat exchangers, control systems, all potential failure points. The Soviets launched several nuclear reactor-powered satellites in the 1,970 seconds and 80 seconds. Most operated for months to a few years before failing. Designing a reactor for century-long operation in deep space is far beyond current capabilities. Solar panels work near stars but are useless in deep space. At Alpha Centauri, 4 light-years from the Sun, sunlight intensity is 16 trillion times weaker than at Earth. Solar panels would generate nanowatts completely inadequate. You might deploy solar panels after arriving at Alpha Centauri, using the local star's light, but panels must survive decades in transit, deploy reliably despite radiation damage and thermal cycling, and generate sufficient power from a star whose spectrum and intensity may differ from the Sun's. Mechanical systems are even more problematic. Reaction wheels spinning flywheels used for attitude control have bearings that wear. Lubrication degrades in vacuum. Eventually, friction increases. Wheels seize, and you lose attitude control. Gyroscopes drift. Accelerometers accumulate errors. Any moving part is a potential failure point. Micrometeorite impacts slowly erode surfaces. Optical components, mirrors, lenses, windows accumulate pits and scratches. After decades of bombardment, optical transmission decreases. Imaging quality degrades. Star trackers become less accurate. Communication laser beams spread wider. Each impact is tiny microns of material removed, but millions of impacts add up. Thermal cycling stresses materials. As the spacecraft moves through space, sunlight heats one side, while the shadow side radiates heat into the cosmic background at 3 Kelvin. Temperature differences of hundreds of degrees develop across the structure. Materials expand and contract. Joints experience stress. Over thousands of thermal cycles, fatigue cracks develop, seals fail. Structures warp. Software presents its own challenges. Code must run for decades without reboots or updates. But code has bugs. Any sufficiently complex program contains errors. Some bugs only manifest under rare conditions that were never tested. When a critical bug triggers during the mission, perhaps after 30 years of operation, the spacecraft might enter a safe mode stop collecting science data, or even lose communication entirely. Radiation causes bit flips in memory, random changes from 0 to 1 or vice versa. Error-correcting codes can detect and fix single-bit errors, but not multiple simultaneous errors. Over decades, enough bit flips accumulate that critical data becomes corrupted. The spacecraft might forget its mission parameters, lose calibration data, or execute corrupted commands that damage hardware. Artificial intelligence systems trained on Earth might behave unpredictably in conditions never encountered during testing. An AI designed to handle spacecraft malfunctions will face situations no human anticipated. If the AI makes a poor decision shutting down a critical system at the wrong time, misinterpreting sensor data, prioritizing the wrong objectives, there is no override, no human intervention, no fix. The AI's decisions are final. Component aging affects everything. Solder joints develop cracks from thermal stress. Capacitors dry out. Transistors develop leakage currents. Wire insulation becomes brittle and cracks. Each component degrades gradually, and systems designed with comfortable margins during ground testing might fail unexpectedly when multiple components have degraded simultaneously during flight. Testing spacecraft for century-long missions is impossible. We cannot run decade-long tests on Earth. The mission would launch before testing completes. Accelerated aging tests simulate years of exposure in months using intense radiation, thermal cycling, and vibration. But accelerated tests do not always predict real-world failure modes accurately. Some problems only appear under actual mission conditions that cannot be replicated on the ground. The spacecraft must diagnose its own failures and implement workarounds autonomously. If a sensor fails, switch to backups. If a computer crashes, reboot and restore from memory. If power drops, prioritize critical systems and shut down non-essential functions. All of this must happen automatically, without instructions from Earth. The software must be sophisticated enough to handle failures engineers never imagined, in combinations never tested. Consider a cascade failure. One system fails, causing increased load on another, which then fails, triggering a third failure. Within minutes, multiple systems are offline. The spacecraft must recognize the cascade, isolate failed systems to prevent further damage, reconfigure around failures, and continue the mission with degraded capabilities. Designing this level of autonomous fault tolerance is extraordinarily difficult, and testing it is nearly impossible. We cannot predict all possible failure combinations. Ultimately, the survival problem comes down to statistics and probability. If each component has a 1% chance of failure per decade, and your spacecraft has 100 critical components, probability says that after a few decades, something will have failed. Redundancy helps, but redundant systems also fail. Eventually, failures accumulate faster than redundancy can compensate. The mission ends not with a dramatic explosion, but with a gradual decay into silence as system after system stops working. The particle collision problem. At high velocities, even empty space becomes dangerous. The interstellar medium is not truly empty. It contains roughly 1 hydrogen atom per cubic centimeter. This sounds sparse. In laboratory terms, it is a near-perfect vacuum, better than anything we can create on Earth. But at relativistic speeds, those sparse atoms become deadly projectiles. Consider a spacecraft traveling at 10% of light speed of 30,000 kilometers per second. A hydrogen atom floating in space is effectively stationary compared to this velocity. From the spacecraft's reference frame, the hydrogen atom is approaching at 30,000 kilometers per second. The kinetic energy of collision is 1/2 mass times velocity squared. For a single hydrogen atom at this speed, the kinetic energy is about 60 MeV million electron volts. That might not sound like much. A single hydrogen atom is tiny. Its mass is 1.67 times 10 to the negative 27 kilograms. But 60 MeV is enough to cause nuclear reactions when the atom strikes the spacecraft's hull. The impact creates a shower of secondary particles, protons, neutrons, pions, gamma rays. These secondaries penetrate deep into the spacecraft, damaging electronics, heating materials, and creating additional radiation hazards. Now scale this up. The spacecraft, traveling at 30,000 kilometers per second, sweeps through space at that velocity. In 1 second, it traverses 30,000 kilometers. The volume of space swept is the cross-sectional area of the spacecraft times the distance traveled. For a spacecraft with a 1 meter square frontal area, that is 30,000 cubic kilometers per second, at 1 hydrogen atom per cubic centimeter, that volume contains 3 times 10 to the 15th atoms, 3 quadrillion atoms. Each second, 3 quadrillion hydrogen atoms strike the spacecraft at 30,000 kilometers per second. Each collision releases 60 MeV. Total energy deposition, 1.8 times 10 to the 23 MeV per second, or about 29 joules per second, 29 watts. This is the power absorbed by just 1 square meter of frontal area from hydrogen alone. Scale up to a larger spacecraft, say 10 meters across, and you absorb 2,900 watts. That is like having 3 electric space heaters running continuously, trying to burn through your hull. This is called erosion heating, and it gets worse at higher velocities. Energy scales with velocity squared. At 20% light speed, the target for breakthrough starshot, the energy quadruples. Each hydrogen atom carries 240 MeV. The spacecraft absorbs not 29 watts per square meter, but 116 watts. At 50% light speed, each atom carries 1,500 MeV, and heating reaches kilowatts per square meter. The spacecraft would glow red hot from friction with the interstellar medium. But hydrogen atoms are not the only hazard. The interstellar medium also contains dust, tiny grains of carbon, silicates, and ice. These grains range from nanometers to micrometers in size. They are rare compared to hydrogen atoms, perhaps 1 grain per 10,000 cubic meters, but they are millions of times more massive than hydrogen atoms. A dust grain 1 micrometer across, about the size of a bacterium, mass is roughly 10 to the negative 15 kilograms. At 10% light speed, its kinetic energy is 450 joules. That is the energy of a baseball thrown at 90 miles per hour, compressed into a particle the size of a bacterium. The impact creates a crater on the spacecraft's surface, shatters surrounding material, and releases the energy as a shock wave that propagates through the hull. Larger grains cause more damage. A 10 micrometer grain carries 45,000 joules, the energy of a car moving at highway speed. 100 micrometer grain, barely visible to the naked eye, carries 45 million joules, equivalent to 10 kilograms of TNT. These impacts do not just pit the surface. They punch holes through thin materials, shatter components, and could potentially destroy a lightweight spacecraft. The distribution of dust grain sizes follows a power law. Small grains are common. Large ones are rare. But rare does not mean absent. Over a journey of 4 light years, a spacecraft with a 1 square meter frontal area might encounter 110 micrometer grains and perhaps 100 micrometer grain. That single large grain impact could end the mission. Shielding helps but adds mass. The traditional approach is a Whipple shield, two thin layers separated by a gap. The first layer shatters incoming particles, spreading their energy over a larger area. The debris cloud then strikes the second layer, which absorbs the remaining energy. This works well for orbital debris at velocities of a few kilometers per second. At tens of thousands of kilometers per second, Whipple shields are less effective. The impact energies are so high that both shield layers vaporize along with the impactor. Advanced shielding concepts use multiple layers with varying materials: aluminum to vaporize impactors, Kevlar to absorb debris, ceramics to block radiation, but every layer adds mass. Protecting a spacecraft against micrometer-scale dust at 10% light speed requires centimeters of shielding. For a spacecraft 10 meters across, that means tons of shielding material, which must be accelerated to cruising speed, which requires more fuel. We return to the rocket equation problem. Some propose orienting the spacecraft so its smallest cross-section faces forward, minimizing collision probability. A needle-shaped spacecraft presents less area than a flat disk. But this complicates design. Solar panels, antennas, and instruments typically need specific orientations that might not align with the optimal hull orientation. And even a needle has a tip that absorbs impacts. Another idea uses consumable shielding material that deliberately vaporizes upon impact, absorbing energy through ablation. This works until the shield is eroded away. For a multi-decade mission, the shield must be thick enough to survive countless impacts. Again, mass requirements explode. Magnetic shielding might deflect charged particles, but does nothing against neutral atoms or dust grains. Electrostatic shields face the same limitation. Plasma shields a cloud of ionized gas ahead of the spacecraft that intercepts and ionizes incoming particles, require energy to maintain and add complexity. The plasma itself creates drag, requiring continuous thrust to maintain velocity. At 20% light speed, proposed for Starshot, the particle collision problem becomes severe. The probe design calls for a sail just atoms thick to minimize mass. But an atom-thick sail will not survive the interstellar medium. Even at the proposed gram-scale mass, a sail measuring meters across presents a large target. Over 20 years of flight, it will accumulate thousands of dust grain impacts. Each impact creates a hole, enough holes, and the sail becomes useless. The Starshot team acknowledges this problem. Their solution is to make the probe small enough and light enough that even with significant damage, it can complete the mission. The sensor package is tiny, perhaps a few grams. If the sail degrades, the probe continues ballistically, no longer able to maneuver but still transmitting data. It is not a solution to the collision problem, it is acceptance of the damage and planning around it. For larger spacecraft, especially crewed missions, the particle collision problem may be insurmountable. Human spacecraft need substantial volume, living space, life support, supplies. This means a large cross-sectional area. Large areas mean more collisions. More collisions require more shielding. Shielding adds mass. Mass requires more propulsion. We spiral back to the energy problem, the interstellar medium. Between the stars lies not emptiness, but a sparse sea of matter and energy that poses unique challenges to any spacecraft attempting interstellar flight. This region, called the interstellar medium, contains gas, dust, cosmic rays, and magnetic fields spread across the vast distances separating stellar systems. Understanding its composition and behavior is essential to comprehending why crossing it at high velocity becomes so problematic. The interstellar medium consists primarily of hydrogen, the universe's most abundant element. Observations from radio telescopes detecting the 21 centimeter emission line of neutral hydrogen reveal an average density of approximately 1 atom per cubic centimeter in the general interstellar medium. This varies considerably depending on location. In dense molecular clouds where stars form, densities reach hundreds or thousands of atoms per cubic centimeter. In the hot, tenuous regions between clouds, densities drop to 1 atom per 10 cubic centimeters or less. Beyond hydrogen, the interstellar medium contains helium at roughly 10% abundance by number, with trace amounts of heavier elements, carbon, nitrogen, oxygen, and metals produced by stellar nucleosynthesis and scattered into space by supernovae and stellar winds. These heavier elements form dust grains when temperatures drop low enough for atoms to condense. Interstellar dust consists primarily of silicates and carbon compounds, with mantles of frozen water, methane, and ammonia deposited on grain surfaces in cold regions. Dust grain sizes range from nanometers to micrometers. The size distribution follows a power law, with small grains vastly outnumbering large ones. A typical interstellar dust grain is about 0.1 micrometers across roughly 1,000th the width of a human hair. These tiny particles absorb and scatter starlight, causing the interstellar reddening and extinction that obscures distant stars when viewed through the galactic plane. The total mass of dust in the interstellar medium amounts to roughly 1% of the gas mass. Yet dust plays a disproportionate role in interstellar chemistry and physics. The interstellar medium is not static. It moves and churns, driven by stellar winds, supernova shock waves, and galactic rotation. Different regions have different temperatures and densities, classified by astronomers into several distinct phases. Cold neutral medium regions have temperatures around 100 Kelvin and densities of tens of atoms per cubic centimeter. Warm neutral medium regions reach 6,000 Kelvin with densities near 1 atom per cubic centimeter. Warm ionized medium zones have temperatures around 8,000 Kelvin. Hot ionized medium regions, heated by supernova shock waves, reach temperatures of millions of Kelvin but have densities of only 0.01 atoms per cubic centimeter. The local interstellar medium surrounding our solar system is part of what astronomers call the local bubble, a region roughly 300 light-years across with lower than average density. The Sun currently moves through a small, dense cloud within this bubble called the local interstellar cloud, which has a density of about 0.3 atoms per cubic centimeter and a temperature of 7,000 Kelvin. Voyager 1 crossed into this truly interstellar medium in 2012, providing the first in situ measurements of the local interstellar environment. Data from Voyager reveals that the interstellar magnetic field near the solar system has a strength of about 2 to 3 microgauss, roughly 100,000th the strength of Earth's surface magnetic field. This weak field nonetheless plays important roles in cosmic ray propagation and plasma physics. The field is not uniform but twisted and tangled by turbulent processes, creating a complex magnetic topology that varies on scales from astronomical units to light years. Cosmic rays fill the interstellar medium high-energy particles, mostly protons, accelerated to near light speed by supernova shock waves and other energetic processes. The cosmic ray energy density in the local interstellar medium is roughly 1 electron volt per cubic centimeter. These particles spiral along magnetic field lines, scattering off magnetic irregularities in a random walk that eventually distributes them throughout the galaxy. The cosmic ray spectrum extends from millions of electron volts to beyond 10, 20 electron volts for the most energetic particles ever detected. For a spacecraft traveling through this medium at relativistic velocities, every component becomes a potential hazard. The hydrogen atoms that pose minimal risk at low speeds transform into penetrating radiation at 10 or 20% light speed. Each collision deposits energy into the spacecraft hull through nuclear reactions, creating showers of secondary particles, pions, muons, gamma rays. These secondaries propagate through the spacecraft, damaging electronics, heating materials, and contributing to radiation dose for any biological passengers or samples. Dust grain impacts at relativistic speeds release energy comparable to explosives. The kinetic energy equation shows that a 1 microgram dust grain, far too small to see with the naked eye, striking a spacecraft at 10% light speed, deposits 450 joules of energy. That equals the energy of a baseball thrown at 90 miles per hour, concentrated into an impact point smaller than a bacterial cell. The resulting crater measures micrometers across, but penetrates deeply into materials, potentially puncturing thin-walled structures or damaging sensitive components. The frequency of such impacts depends on dust, density, and spacecraft cross-sectional area. Typical interstellar dust densities are roughly 10 - 24 grams per cubic centimeter. For a spacecraft with 1 square meter frontal area traveling at 10% light speed, this translates to approximately 1 dust grain impact per day. Over a 40-year journey to Alpha Centauri, the spacecraft would endure roughly 15,000 impacts. Each creates a small crater. Accumulated damage from thousands of impacts degrades optical surfaces, erodes protective coatings, and gradually weakens structural elements. Magnetic fields in the interstellar medium interact with any charged components of the spacecraft. Electrical currents in power systems experience Lorentz forces from the magnetic field. Charged particle beams used for propulsion or communication deflect slightly. These effects are small but accumulate over astronomical distances. Precise navigation requires accounting for magnetic field interactions, yet the field strength and direction along the trajectory cannot be measured in advance. They vary unpredictably across light years. The interstellar medium also contains molecular hydrogen H2 in addition to atomic hydrogen. Molecular hydrogen is more difficult to detect because it lacks a strong emission line at radio wavelengths. Observations using ultraviolet absorption lines against background stars reveal that molecular hydrogen contributes significantly to the total gas density in certain regions, particularly in molecular clouds. A spacecraft trajectory might pass through regions where molecular hydrogen dominates, doubling the effective gas density and the associated collision hazards. Temperature variations in the interstellar medium create density variations through the ideal gas law. Colder regions contract to higher densities, while hot regions expand. A spacecraft might traverse multiple phases of the interstellar medium during its journey, passing through warm neutral medium for part of the voyage, then entering a cold molecular cloud for several light months, then emerging into hot ionized medium. Each transition changes the collision rate, radiation environment, and drag forces experienced by the spacecraft. Some proposals suggest using the interstellar medium as a resource rather than viewing it purely as a hazard. Interstellar ramjets would scoop hydrogen from space and fuse it for propulsion, as discussed earlier. But even if fusion ramjets prove impractical, understanding the interstellar medium remains essential for any mission planning. Trajectories might be optimized to avoid the densest regions, trading additional distance for reduced collision damage. Or missions might time their passages to minimize exposure to newly ejected supernova material or stellar wind enhancements. The boundary between the solar wind and the interstellar medium, the heliopause, lies roughly 120 astronomical units from the Sunday. This marks the edge of the Sun's influence and the beginning of true interstellar space. Beyond this boundary, spacecraft leave behind the protective bubble of the heliosphere and enter an environment no human-made object visited until Voyager 1 crossed in 2012. Every interstellar mission will spend more than 99.9% of its journey time in this alien environment, far from any star's moderating influence. The quantum limits of computation. Any interstellar spacecraft, whether crewed or robotic, requires onboard computation. Navigation systems calculate trajectories. Guidance systems control attitude and propulsion. Communication systems encode and decode data. Science instruments process measurements. Life support systems regulate the environment. All of these functions demand computers that must operate reliably for decades or centuries without ground support. Understanding the limits of computation, including fundamental quantum limits, reveals another layer of challenges facing interstellar missions. Modern computers use transistors etched onto silicon chips. As of 2025, leading-edge processors contain transistors measuring just a few nanometers across, approaching the size of individual molecules. Moore's law, the observation that transistor counts double roughly every 2 years, has driven exponential improvements in computing power for decades. But this exponential growth cannot continue indefinitely. Physical limits rooted in quantum mechanics eventually halt miniaturization. At dimensions below approximately 5 nanometers, quantum effects dominate transistor behavior. Electrons tunnel through barriers that should be impassable according to classical physics. This quantum tunneling causes leakage currents that prevent transistors from maintaining distinct on and off states. The fundamental uncertainty principle of quantum mechanics limits how precisely we can confine electrons in space and energy. These quantum limits, not merely engineering challenges, set absolute boundaries on transistor miniaturization. Current projections suggest that silicon transistor scaling will end around 2030 at feature sizes near 2 nanometers. Beyond this point, alternative computing architectures become necessary. Candidates include carbon nanotube transistors, spintronics devices, quantum computers, and photonic processors. Each offers potential advantages but faces its own limitations and development challenges. For space applications, radiation hardness is paramount. Cosmic rays and solar energetic particles strike computer memory, flipping bits from 0 to 1 or vice versa. These single event upsets corrupt data and can crash programs. Radiation-hardened processors use multiple techniques to mitigate this. Error-correcting codes, redundant transistors, special fabrication processes, but radiation hardening trades off against performance. Radiation-hard chips lag commercial processors by a decade or more in capability. An interstellar mission requires computers that function for 50 to 100 years in the harsh radiation environment beyond the heliosphere. Total ionizing dose accumulates continuously. Each cosmic ray impact displaces atoms in the silicon crystal, creating permanent damage. Eventually, transistors fail. No amount of error correction can compensate for permanent physical destruction of the device. Redundancy extends operational life. Triple redundant computers vote on every decision, with majority ruling. When one fails, the remaining two continue. When the second fails, the last computer operates alone until it too succumbs to radiation. This approach works, but adds mass, power consumption, and complexity. And it merely delays the inevitable. After enough time, all computers fail. Some proposals suggest using mechanical computing devices for critical functions. Mechanical computers built from gears and linkages operated reliably before electronics existed. They are immune to radiation. Cosmic rays do not flip gear teeth, but mechanical computers are slow, bulky, and limited in computational power. They cannot handle the data processing demands of modern spacecraft instruments, and mechanical parts suffer their own failure modes: friction, fatigue, and wear. Quantum computing offers fascinating possibilities, but faces severe obstacles in space applications. Quantum computers exploit superposition and entanglement to perform certain calculations exponentially faster than classical computers. But quantum bits, qubits, are extraordinarily fragile. They require near absolute zero temperatures, electromagnetic isolation, and freedom from vibration. Cosmic rays destroy quantum coherence instantly. Current quantum computers occupy entire laboratories. Miniaturizing them to spacecraft scale while maintaining quantum coherence in the space environment seems impossible with any foreseeable technology. Photonic computing using light instead of electrons might offer better radiation tolerance. Photons are not charged particles, so cosmic rays affect them less directly. But photonic processors still require detectors and modulators made from semiconductors vulnerable to radiation. And photonic computing remains in early research stages, far from commercial deployment. The computational demands of interstellar missions are substantial. Navigation at high velocity requires processing star tracker data to measure position and orientation. This involves image recognition algorithms identifying stars against background noise, matching observed patterns to catalogs containing billions of stars, calculating position solutions from multi-star triangulation, and applying relativistic corrections for aberration and time dilation, all in real time, continuously, for decades. Communication systems must encode data with sophisticated error correction, adapt transmission parameters to changing signal-to-noise ratios, maintain precise timing for synchronization, and manage transmission schedules to maximize data return while minimizing power consumption. These tasks require significant processing power, sustained over mission duration. Autonomous decision-making demands even more computation. When systems fail, the spacecraft must diagnose problems, identify solutions, implement repairs or workarounds, and resume operations, all without human intervention. This requires AI capabilities far exceeding current autonomous systems. The software must be sophisticated enough to handle situations never anticipated by designers, yet simple enough to run on radiation-hardened processors with limited computational power. Data storage faces similar challenges. Science instruments generate terabytes of data during observations. This data must be stored reliably until it can be transmitted to Earth. But all memory is vulnerable to radiation. Dynamic RAM loses data within milliseconds without refresh. Static RAM retains data longer, but still requires power. Flash memory degrades after a finite number of write cycles, and all semiconductor memory accumulates radiation damage that eventually causes failures. Magnetic storage hard drives and tape might resist radiation better than semiconductor memory, but magnetic media suffer mechanical wear. Hard drive spindles and read, write, heads have finite lifetimes. Tape transports, jam. In both cases, moving parts mean eventual failure. Optical storage on media, like CDs or DVDs, is radiation hard and has no moving parts. But writing and reading requires lasers and mechanical positioning systems that themselves fail. Some proposals suggest using DNA molecules for data storage. DNA naturally stores biological information with extraordinary density and remarkable stability. Synthetic DNA could encode digital data, providing storage that lasts millennia without power. But reading DNA requires chemical processing incompatible with spacecraft mass and power budgets. Writing is even more challenging. DNA storage remains a laboratory curiosity, nowhere near practical deployment. The computational challenge extends to software reliability. Code must execute flawlessly for decades, but all complex software contains bugs. NASA's Mars rovers run software containing millions of lines of code. Despite exhaustive testing, bugs occasionally manifest during operations. On Mars, ground controllers can upload patches and workarounds. For interstellar missions, the software must be perfect from the start. No updates are possible once the spacecraft travels beyond communication range, where round-trip signal times exceed mission durations. Formal verification methods can mathematically prove software correctness, but only for small programs. Proving correctness of a complete spacecraft operating system containing millions of lines of code remains beyond current capabilities. We can test exhaustively, but testing never guarantees absence of bugs, only their presence. Radiation-induced bit flips corrupt software as readily as data. A cosmic ray striking program memory might change a single instruction, causing unpredictable behavior. Error-correcting codes detect and fix these corruptions, but error correction itself requires additional code that might contain bugs or be corrupted by radiation. The problem becomes recursive. Quantum limits also constrain communication bandwidth. The Bekenstein bound, derived from black hole thermodynamics, sets a fundamental maximum on information density, roughly 1069 bits per kilogram per meter. For any communication system, this translates to limits on how much information can be transmitted with given energy and mass budgets. While these limits exceed any practical communication system by many orders of magnitude, they represent absolute boundaries we cannot overcome, regardless of future technological development. More immediately relevant is the Shannon-Hartley theorem, which limits communication capacity based on signal, power, and noise. To transmit more data, you need more power or more bandwidth. But power comes from limited energy sources, and available bandwidth is constrained by antenna sizes and frequencies. There is no way around these limits. They follow from information theory itself. The stellar wind gauntlet. Stars are not passive beacons shining quietly in the darkness. They are active, dynamic objects that constantly expel material into space through stellar winds. Our Sun ejects roughly 1 million tons of matter every second in the form of charged particles, primarily protons and electrons, that stream outward at velocities between 400 and 800 kilometers per second. This creates a bubble of solar influence extending roughly 120 astronomical units from the Sun, beyond which the interstellar medium takes over. Alpha Centauri is not one star, but three. Alpha Centauri A and B form a binary pair, orbiting each other every 80 years at distances varying between 11 and 36 astronomical units. Proxima Centauri, the closest of the three, orbits the binary pair at a distance of about 13,000 astronomical units. Each of these stars generates its own stellar wind, creating a complex and dynamic radiation environment that any approaching spacecraft would need to traverse. Alpha Centauri A is slightly larger and more luminous than our Sun, classified as a G-type main sequence star. Its stellar wind is probably comparable to or slightly stronger than the solar wind. Alpha Centauri B is a K-type star, smaller and cooler, with a correspondingly weaker stellar wind. But Proxima Centauri presents a different challenge entirely. Proxima Centauri is a red dwarf, a small, cool M-type star with only about 12% the mass of the Sunday red dwarfs, are known for violent stellar activity. They produce enormous flares that can temporarily increase their luminosity by factors of 10 or more. During these flares, the stellar wind intensifies dramatically, ejecting bursts of high-energy particles into space. Proxima Centauri has been observed to produce flares with energies exceeding 10 or 33 ergs, 100 times more powerful than the most intense solar flares ever recorded. These flares occur unpredictably. A spacecraft approaching Proxima Centauri might encounter normal stellar wind conditions one day and be engulfed in a radiation storm the next. The particle flux during major flares can exceed normal levels by factors of 1,000 or more. Electronics would be bombarded, radiation doses to any biological material would spike to lethal levels within hours. Shielding that adequately protects during quiescent periods might be overwhelmed during flare events. The stellar wind also carries embedded magnetic fields. As the wind expands outward, these magnetic fields create complex structures, current sheets, magnetic loops, and turbulent regions where field lines reconnect and release energy. A spacecraft traversing these regions would experience varying magnetic field strengths and directions, complicating navigation and potentially inducing electrical currents in conductive structures. Near the stars themselves, within a few astronomical units, the stellar wind density increases dramatically. If a mission required close approach to Alpha Centauri A or B for gravity assist maneuvers or orbital insertion, the spacecraft would enter regions where wind particle density reaches millions per cubic centimeter, 1,000,000 times denser than the general interstellar medium. At relativistic approach velocities, this creates an erosive environment that ablates surface materials and generates intense heating through particle bombardment. The interaction between stellar winds and interstellar magnetic fields creates bow shocks regions where the wind suddenly decelerates as it encounters the resistance of the surrounding medium. These bow shocks can extend many astronomical units from the star, forming turbulent transition zones filled with energetic particles accelerated by shock waves. Spacecraft would need to cross these bow shocks during approach, exposing them to enhanced radiation levels precisely when they are closest to the destination and most vulnerable to accumulated damage from the long journey. Stellar wind composition varies with stellar activity cycles. During periods of high activity, the wind contains increased fractions of heavy ions, carbon, nitrogen, oxygen, iron. These heavier particles carry more kinetic energy at given velocities and cause more severe radiation damage when they strike materials. Long-term monitoring would be needed to predict stellar activity levels at arrival time, but for journeys lasting decades, such predictions become increasingly uncertain. The triple star system creates interference patterns where the three stellar winds interact. Where winds collide, they form compressed regions of enhanced density and turbulence. These interaction zones shift position as the stars orbit, creating a dynamic radiation topology that changes over timescales of years to decades. A trajectory planned to avoid the worst radiation zones might find those zones have moved by the time the spacecraft arrives. Communication becomes more difficult when stellar wind density increases. Radio waves scatter off free electrons in the wind, causing signal degradation and limiting achievable data rates. During flare events, the enhanced particle density can temporarily block radio communication entirely, preventing the spacecraft from transmitting critical data during the most scientifically interesting periods. Some proposals suggest using the stellar wind as a braking mechanism. A magnetic sail could interact with the stellar wind, extracting momentum to decelerate the spacecraft without expending propellant. But this requires enormous magnetic field structures and only works in regions where wind density is sufficient within a few astronomical units of the star. It provides minimal braking at interstellar distances where most deceleration would need to occur. The stellar wind also carries away angular momentum from the stars, causing them to spin down over billions of years. This process is well understood for single stars, but becomes complex in binary systems, where tidal interactions between the stars affect rotation rates. The long-term evolution of stellar wind properties over mission timescales spanning decades adds another layer of uncertainty to mission planning. Understanding stellar winds requires both observational astronomy and theoretical modeling. Observations from space-based telescopes reveal wind properties for our Sun and some nearby stars, but detailed characterization of Alpha Centauri's winds remains incomplete. Models extrapolate from solar data, but uncertainties remain. A spacecraft arriving at Alpha Centauri might encounter conditions significantly different from predictions made decades earlier when the mission was designed. The stellar wind gauntlet represents an often overlooked obstacle to interstellar travel. While less dramatic than the energy requirements of acceleration or the challenges of interstellar dust collisions, stellar winds create a hostile environment that must be traversed at journey's end, precisely when spacecraft systems are most degraded from decades of operation and accumulated radiation damage. The materials science frontier. Every spacecraft is ultimately limited by the materials from which it is constructed. Metals, ceramics, polymers, and composites each have specific properties: strength, density, thermal conductivity, radiation resistance that determine what the spacecraft can do and how long it can survive. For interstellar missions, material requirements exceed anything currently achievable, pushing against fundamental limits of atomic bonds and crystal structures. Consider structural materials. A spacecraft must be strong enough to withstand launch loads, light enough to be accelerated efficiently, and tough enough to survive decades of thermal cycling, radiation exposure, and particle impacts. Aluminum alloys, the workhorse of aerospace engineering, provide good strength to weight ratios, but suffer from gradual radiation damage. High-energy particles displace atoms from the crystal lattice, creating defects that accumulate over time. Eventually, the material becomes brittle and prone to crack propagation. Titanium alloys offer better radiation resistance than aluminum, but are denser, reducing mass efficiency. Steel is stronger still, but heavier. Exotic alloys incorporating rare elements like niobium or tantalum can be engineered for specific properties, but these materials are expensive, difficult to fabricate, and often poorly characterized for long-duration space exposure. Carbon fiber composites provide exceptional strength to weight ratios better than any metal. They are used extensively in modern spacecraft structures. But carbon fibers are susceptible to atomic oxygen erosion in low Earth orbit and to radiation-induced degradation during long-duration missions. The polymer matrix binding the fibers together breaks down under ultraviolet radiation and particle bombardment. After sufficient exposure, the matrix loses cohesion and the composite fails. Researchers have developed radiation-resistant polymers using aromatic molecular structures that dissipate energy more effectively. Polyamides like Kapton withstand radiation doses that destroy most organic materials. But even these advanced polymers have limits. Total ionizing dose accumulates continuously in interstellar space. Given enough time, all organic materials degrade. A 40-year mission to Alpha Centauri exposes materials to radiation doses exceeding anything experienced by spacecraft in Earth orbit or even deep space missions to the outer planets. Thermal protection materials face extreme challenges. A spacecraft traveling at 10% light speed must dissipate heat generated by interstellar medium collisions and by onboard systems operating continuously for decades. Radiators are essential but face their own material constraints. They must have high thermal conductivity to transport heat efficiently. high emissivity to radiate heat into space, and resistance to erosion from dust impacts. Traditional radiator materials like aluminum or copper gradually degrade. Each dust grain impact creates a small crater, reducing effective surface area. Thousands of impacts over years erode the surface, decreasing radiator efficiency. Coatings can protect against erosion but add mass, and may themselves degrade under radiation. Some advanced concepts propose using liquid metal radiators that can self-heal after impacts, but these systems are complex and unproven. Propellant tanks present unique material challenges. Cryogenic propellants like liquid hydrogen must be stored at temperatures near absolute zero. Tank materials must maintain structural integrity at these extreme temperatures while preventing heat leak from the environment. Multi-layer insulation helps, but is vulnerable to damage from particle impacts. Even tiny perforations allow heat to penetrate, causing propellant boil-off that accumulates over decades, potentially depleting fuel supplies before the mission concludes. Optical materials for mirrors, lenses, and solar panels degrade under radiation and dust erosion. Spacecraft cameras and telescopes require precise optical surfaces that maintain their shape and smoothness. But each dust grain impact creates surface roughness. Accumulated damage over years scatters light, reducing image quality. Protective windows can shield optics, but themselves become scratched and pitted, eventually requiring replacement difficult or impossible during an interstellar mission. Solar cells convert sunlight to electricity through semiconductor physics, but radiation damage degrades their efficiency. High-energy particles displace atoms in the semiconductor crystal, creating defects that trap charge carriers and reduce current output. Solar cells on long-duration missions to Jupiter and Saturn show measurable degradation after just a few years. For decades-long interstellar missions, solar cell efficiency might drop by 50% or more, forcing oversized solar arrays at departure to compensate for predicted degradation. Nuclear materials for radioisotope power systems face similar degradation. Plutonium-238, used in radioisotope thermoelectric generators, has a half-life of 88 years. During a 40-year mission, about 28% of the plutonium decays, reducing power output correspondingly. The decay products, uranium and other isotopes, remain in the fuel, potentially altering thermal properties and causing structural changes. Thermoelectric converters that transform heat to electricity also degrade over time as material properties drift. Lubricants present unexpected challenges. Mechanical systems require lubrication to prevent wear, but most lubricants are organic compounds that degrade under radiation and outgas in vacuum. Traditional oils and greases would not survive decades in space. Solid lubricants like molybdenum disulfide work better but gradually wear away through mechanical action. Eventually, unlubricated surfaces grind against each other, generating wear debris that can jam mechanisms. Sealants and adhesives hold spacecraft together, bonding dissimilar materials and sealing pressure vessels. These materials are typically polymers that, like all organic materials, degrade under radiation. A seal that holds pressure perfectly at mission start might develop leaks after years of radiation exposure. Redundant sealing and careful material selection can extend lifetime, but all seals eventually fail. Even inert materials like glass and ceramics are not immune to degradation. High-energy cosmic rays create atomic displacements in crystalline structures. These displacement cascades alter material properties over time. Ceramics may become more brittle. Glass may change its optical properties. The changes are subtle but accumulate relentlessly over decades of continuous exposure. Researchers are developing new materials specifically for long-duration space missions. Single crystal alloys eliminate grain boundaries where cracks initiate. Self-healing materials incorporate capsules of repair agents that release when cracks form. Metamaterials with engineered nanostructures provide properties impossible in conventional materials. But all of these remain in laboratories. None have been proven in actual space environments for extended durations. The fundamental problem is time. We cannot test materials for 40 years before flying them on 40-year missions. Accelerated testing tries to simulate decades of exposure in shorter times by increasing radiation dose rates or thermal cycling frequencies. But accelerated tests may not accurately predict long-term behavior. Materials can respond differently to accumulated low-level damage versus rapid high-level damage. Materials science sets absolute limits on what spacecraft can do and how long they can survive. Every component eventually fails. Every material eventually degrades. Engineers can design for redundancy, select the best available materials, and minimize exposure to damaging environments. But they cannot eliminate material degradation entirely. The laws of thermodynamics ensure that all structures tend toward disorder. For interstellar missions measured in decades, material degradation may prove as insurmountable as energy limitations or propulsion challenges. The biological containment problem. If any interstellar mission carries life, whether human crews, plant experiments, or even bacterial samples, it introduces biological challenges that transform mission design completely. Living organisms have requirements incompatible with spacecraft constraints. They need food, water, oxygen, waste processing, temperature control, and protection from radiation. More fundamentally, they evolve and change in ways that cannot be fully predicted or controlled over multi-decade timescales. Begin with the simplest case, carrying bacterial samples for scientific study. Bacteria are extraordinarily resilient, capable of surviving extreme conditions. Some species tolerate high radiation, extreme temperatures, desiccation, and vacuum. They can enter dormant states lasting years. This makes them attractive for space missions. They might survive the journey without active life support. But therein lies a problem. They might survive anywhere. Planetary protection protocols require that spacecraft visiting potentially habitable worlds must be sterilized to prevent contaminating those worlds with Earth life. The standards are stringent. Fewer than 300,000 bacterial spores on surfaces, with special cleaning for components that might contact liquid water. But achieving complete sterilization is nearly impossible. Bacteria infiltrate tiny crevices, seal themselves inside materials, form biofilms that resist cleaning. Some always survive. For missions to Alpha Centauri, whether to the stars themselves or to any planets that might orbit them, the planetary protection challenges multiply. The journey takes decades. During that time, any surviving bacteria could reproduce if they find suitable conditions. Spacecraft always contain organic materials that bacteria can metabolize: lubricants, polymers, adhesives. Water, essential for spacecraft cooling systems and potentially for human life support, provides an ideal bacterial growth medium if contamination occurs. A spacecraft carrying even a small bacterial population would become an incubator during decades of flight. Bacteria reproduce exponentially when conditions permit. A single bacterial cell can become billions within days if nutrients and temperature allow. These bacteria would colonize every available niche inside the spacecraft, forming biofilms on surfaces, clogging filters, corroding materials, and potentially producing toxic metabolic byproducts. Worse, bacteria evolve. Over thousands of generations during a multi-decade mission, bacterial populations would adapt to spacecraft conditions through natural selection. They might develop resistance to disinfectants. They might evolve to metabolize unusual materials. They might become more aggressive, growing faster and spreading more readily. The bacteria arriving at Alpha Centauri could be significantly different from those that departed Earth, potentially more dangerous and harder to control. If the mission includes human crews, biological challenges intensify dramatically. Humans are ecosystems. Each person carries trillions of microorganisms, bacteria, fungi, viruses, in the gut, on the skin, in the mouth. These microbiomes are essential for health, aiding digestion, training immune systems, and preventing colonization by pathogens. But in the closed environment of a spacecraft, human microbiomes would interact, exchange genetic material, and evolve together. Research on the International Space Station shows that the station's microbial population changes over time. Species that thrive in the station environment, able to tolerate low humidity, grow on metal and plastic surfaces, and resist cleaning protocols, come to dominate. Some of these are opportunistic pathogens, organisms that normally don't cause disease but can infect people with weakened immune systems. Astronauts returning from long-duration missions sometimes experience immune system changes that temporarily increase susceptibility to infection. For a 40-year interstellar mission, these dynamics would play out over far longer timescales. The spacecraft microbiome would evolve into something unique, potentially quite different from Earth microbial communities. Crew members would continuously exchange microbes with each other and with the environment. By mission end, the microbial populations inside human bodies and throughout the spacecraft might bear little resemblance to those that departed. This creates unpredictable health risks. Organisms that were harmless at mission start might evolve virulence, the ability to cause disease. Immune systems adapted to Earth pathogens might struggle with novel organisms evolved in the spacecraft environment. Antibiotics carried from Earth might prove ineffective against bacteria that evolved resistance during the decades-long journey. The crew could face infectious disease outbreaks with no possibility of medical evacuation or resupply of medications. Food production amplifies biological challenges. If the mission carries plants to supplement food supplies a necessity for very long missions, where stored food would degrade, those plants also carry microbiomes. Plant-associated bacteria and fungi could escape cultivation systems and colonize other parts of the spacecraft. Some plant pathogens also affect humans. Cross-contamination between agricultural and habitat modules could spread diseases in both directions. Genetic engineering might offer solutions. Bacteria could be engineered to produce useful products, vitamins, medications, structural materials. Plants could be optimized for spacecraft growth conditions. But engineered organisms also evolve. The modifications carefully designed on Earth might be lost through mutation during decades in space. Or organisms might evolve in unexpected directions, potentially developing traits that make them harder to control. Quarantine becomes impossible during interstellar missions. On Earth, if a disease outbreak occurs, we can quarantine infected individuals and sterilize contaminated areas. But in a spacecraft, everyone shares the same air and water recycling systems. Pathogens spread rapidly through these shared systems. There is nowhere to isolate infected crew members effectively. The entire spacecraft becomes contaminated if serious pathogens emerge. Some proposals suggest freezing biological samples or using induced hibernation to avoid active biological processes during flight. But freezing is not a permanent solution. Frozen samples still experience radiation damage that accumulates over decades, and the freezing equipment itself must operate reliably for the entire mission duration. A single mechanical failure could thaw samples, allowing biological activity to resume uncontrollably. If a mission intends to establish any presence at Alpha Centauri, a base, a colony, or even just conducting biological experiments on any discovered planets, the biological containment problem becomes existential. Any Earth organism released into an alien environment could fundamentally alter that environment. If life already exists there, contamination might harm or destroy it before we even discover it. If life doesn't exist, we might forever lose the opportunity to study a genuinely sterile planetary environment. The ethical implications are profound. Do we have the right to contaminate another star system with Earth life? What if Alpha Centauri has planets with their own biospheres? Should we risk disrupting them? And what if we succeed in establishing Earth life there? Have we begun inevitable biological colonization of the galaxy, or committed an act of irreversible environmental destruction on a cosmic scale? Biological containment for interstellar missions is not merely a technical challenge. It touches on fundamental questions about the nature of life, the ethics of exploration, and humanity's relationship with the universe. Unlike purely physical challenges that might be solved through better engineering, biological challenges involve living systems that by their very nature resist control, evolve unpredictably, and spread whenever possible. The ancient imperative of life to survive and reproduce makes perfect biological containment over decades-long missions effectively impossible with any technology we can currently envision. The economics of the impossible. Interstellar missions are not just technically challenging, they are economically absurd. The costs would dwarf any project humans have ever attempted, requiring resources on scales that strain comprehension. Understanding why interstellar missions are economically impossible reveals that even if technical challenges were somehow overcome, financial reality provides an independent barrier, equally insurmountable. Consider the Apollo program, humanity's most expensive space achievement. From 1961 to 1972, NASA spent approximately $25 billion on Apollo, equivalent to about $280 billion in 2025 dollars when adjusted for inflation. This bought 12 crewed launches, 6 moon landings, and the safe return of all crew members. The effort required mobilizing a significant fraction of American industrial capacity, employing 400,000 workers at peak, and sustaining political will across 3 presidential administrations. Apollo took humanity 380,000 kilometers from Earth, less than 1/10,000,000th the distance to Alpha Centauri. The journeys lasted days, not decades. The spacecraft massed a few tens of tons, not thousands. No new physics was required, no materials beyond existing technology, no propulsion systems that existed only in theory. Yet Apollo barely succeeded and was cancelled when costs became unsustainable politically and economically. Scale Apollo up by the factors required for an Alpha Centauri mission. If costs scaled merely linearly with distance, which drastically underestimates the true scaling, a mission 10 million times farther would cost 10 million times more, $2.8 quadrillion. That is roughly 30 times current global GDP. The entire economic output of humanity for 30 years devoted exclusively to a single interstellar spacecraft. But costs do not scale linearly with mission difficulty. They scale exponentially, or even worse. Developing new propulsion technologies requires decades of research, costing hundreds of billions before a single prototype flies. Fusion propulsion has consumed billions in research, over 70 years without producing a working engine. Antimatter production, if scaled to mission-relevant quantities, would require global-scale energy infrastructure costing trillions. The spacecraft itself would cost far more than Apollo hardware. Instead of a relatively simple capsule and lunar module, an interstellar spacecraft needs multi-megawatt power systems, radiation shielding massing thousands of tons, closed-loop life support sustaining crew for decades, autonomous decision-making systems beyond current AI capabilities, and redundancy in every system because repair and resupply are impossible. Development costs for such systems would easily exceed trillions of dollars. Manufacturing presents additional costs. Building a spacecraft massing thousands of tons from exotic materials requires facilities that don't exist. Construction might take place in orbit to avoid fighting Earth's gravity, but orbital construction infrastructure itself would cost hundreds of billions to establish. Every component must be launched from Earth at current costs of roughly $10,000 per kilogram. Launching a 10,000-ton spacecraft requires 100 million kilograms reaching orbit, costing $1 trillion at current launch prices, even before considering the spacecraft itself. Launch costs might decline with reusable rockets and mass production, but they cannot reach zero. Energy requirements impose absolute minimum costs. Lifting 1 kilogram to low Earth orbit requires at least 33 megajoules of energy. That's physics, not economics. At typical energy costs, this translates to absolute minimum costs around $100 per kilogram, and practical systems will cost more due to inefficiencies, hardware amortization, and operational overhead. The mission requires not just one spacecraft, but supporting infrastructure. Ground stations to communicate across light years need enormous antennas, perhaps kilometers in diameter, and high-power transmitters. These might cost billions per station, and multiple stations are needed for redundancy and continuous coverage as Earth rotates. Tracking and navigation systems must monitor the spacecraft position to within meters across light-year distances, requiring interferometric arrays of radio telescopes scattered across the globe or stationed throughout the solar system. The mission duration creates unique economic challenges. A 40-year mission to Alpha Centauri requires 40 years of ground support, engineers analyzing telemetry, scientists interpreting data, controllers sending commands, administrators managing budgets. How do you fund an organization continuously for 4 decades? Political priorities shift. Economies cycle through recession and growth. Future generations might decide the mission is not worth continued funding and simply turn off the ground stations, abandoning the spacecraft in deep space. Historical precedent suggests this is likely. No human institution has sustained continuous funding for 40 years on a single project without compelling near-term returns. Even Apollo lasted barely 11 years from Kennedy's announcement to the final mission. The International Space Station has operated for 25 years, but required continuous justification and nearly faced cancellation multiple times. A mission with no possibility of returns for 4 decades would struggle to maintain funding across the political and economic disruptions that inevitably occur over such timescales. Opportunity cost is staggering. Money spent on interstellar missions cannot be spent on other priorities. Healthcare, education, infrastructure, poverty reduction, climate change mitigation. Which has greater value to humanity? Sending one spacecraft to Alpha Centauri, or providing clean water to 1 billion people? Curing diseases that kill millions annually? Developing sustainable energy that prevents environmental collapse? From a utilitarian perspective, interstellar missions cannot justify their costs when earthbound needs remain unmet. Alternative space projects offer far better return on investment. Robotic missions to explore the solar system cost millions to low billions and return immediate scientific value. Space telescopes costing a few billion revolutionize our understanding of the universe. Even ambitious projects like Mars colonization, though extraordinarily expensive, would cost orders of magnitude less than interstellar missions and offer tangible benefits like resource utilization and expansion of human civilization within our solar system. Some proponents argue that interstellar missions would drive technological spin-offs that benefit broader society, much as Apollo spurred advances in computing, materials, and systems engineering. But Apollo's return on investment is debatable even for a successful project that cost a fraction of GDP. An interstellar mission costing orders of magnitude more would need to generate proportionally greater benefits to justify the expense implausible, when the same research could be conducted at far lower cost without actually flying the flying mission. Private funding seems equally impossible. No corporation or individual has wealth on the scales required trillions of dollars, and private entities demand returns on investment within years or at most decades. An interstellar mission offers no financial returns ever. It generates no products to sell, no resources to exploit, no patents to license. It is purely an expense with zero economic benefit to any private investor. No rational economic actor would fund such a mission. Philanthropists might support interstellar missions for prestige or idealistic reasons, but philanthropic funding is limited. Total global philanthropic giving is roughly $500 billion annually, most directed to urgent human needs. Convincing philanthropists to redirect substantial fractions of their giving to interstellar missions would require arguing that sending a spacecraft to Alpha Centauri benefits humanity more than feeding the hungry, healing the sick, or educating the young, a difficult ethical case to make. International cooperation might pool resources, but historical examples are not encouraging. The International Space Station required cooperation among 15 nations and still cost roughly $150 billion over 30 years, a rounding error compared to interstellar mission costs. Achieving agreements among dozens of nations to fund a project costing tens of trillions with no returns for decades and requiring sustained cooperation across political upheavals and economic crises seems fantastical. The navigation precision paradox. Navigating across interstellar distances requires pointing accuracy and trajectory precision that exceeds any capability humans have demonstrated. Small errors accumulate over light years, transforming minor inaccuracies into mission-killing deviations. Understanding the navigation challenges reveals that even if all other problems were solved, simply arriving at the intended destination would test the absolute limits of measurement and control. Consider navigation near Earth. GPS satellites orbit at 20,000 kilometers altitude and provide position accuracy of a few meters. This seems precise, but it represents positional uncertainty of roughly 1 part in 10 million 0.00001% error relative to orbital radius. For interstellar navigation, this accuracy is grotesquely insufficient. Alpha Centauri lies 4.37 light-years distant, roughly 41 trillion kilometers. A positional error of 1 part in 10 million translates to uncertainty of 4.1 billion kilometers larger than the diameter of Neptune's orbit. The spacecraft might miss the entire star system. To achieve even crude targeting of individual stars requires navigation accuracy better than 1 part in a billion. 1/10,000th the uncertainty tolerable for GPS. Navigation requires knowing both position and velocity with high precision. Position errors cause the spacecraft to miss the target. Velocity errors cause it to arrive at the wrong time or pass through the system too rapidly to conduct useful observations. These errors are coupled a small velocity error accumulates into large position error over time. During a 40-year journey, even a velocity error of 1 millimeter per second compounds into position error of 1.3 million kilometers. Measuring spacecraft position in deep space relies on radio tracking. Ground stations transmit signals to the spacecraft, which returns them. The round-trip time reveals the distance with precision limited by clock accuracy and signal processing. Measuring velocity requires observing Doppler shifts in the radio signal as the spacecraft moves away. Its transmitted frequency shifts lower proportionally to velocity. These techniques work well within the solar system, where round-trip light times are minutes to hours. But as the spacecraft travels light years from Earth, signal delays stretch to years. It takes 4.37 years for a signal to reach Alpha Centauri, plus another 37 years for the response to return. Navigation updates based on radio tracking would arrive nearly 9 years delayed, useless for making course corrections during the approach to Alpha Centauri. The spacecraft must navigate autonomously using star sights and inertial guidance. Star trackers photograph the sky, identify known stars by comparing observed patterns to catalogues, and calculate position based on apparent star positions. This technique, called celestial navigation, has guided sailors for centuries and spacecraft for decades. But interstellar distances demand precision far beyond anything previously required. Star positions shift due to parallax apparent displacement as viewing angle changes. From Earth, nearby stars show parallax of less than 1 arc-second, 1/3,600th of a degree. At interstellar distances, parallax becomes the primary navigation reference. The spacecraft must measure star positions with precision better than 1 milliarc-second, 1,000th of an arc-second, to determine its position accurately relative to surrounding stars. Achieving milliarc-second astrometry requires large telescopes with precise pointing and careful calibration. The spacecraft must distinguish true star position from instrumental effects, atmospheric refraction, if operating within any stellar system, and relativistic aberration caused by the spacecraft's high velocity. At 10% light speed, aberration shifts apparent star positions by roughly 6 degrees, far larger than the actual parallax being measured. Correcting for aberration requires knowing the spacecraft velocity extremely precisely, creating a circular dependency where position accuracy depends on velocity accuracy, which depends on position accuracy. Inertial guidance systems use accelerometers to measure every acceleration the spacecraft experiences, integrating these measurements over time to track position and velocity changes. But accelerometers drift, small systematic errors accumulate. The finest inertial navigation systems drift at rates of roughly 1 nautical mile per day on Earth. Over 40 years in space, this drift accumulates to hundreds of thousands of kilometers of position, uncertainty unacceptable for interstellar navigation. The spacecraft also experiences accelerations from unexpected sources. Outgassing from materials releases tiny amounts of gas, producing small thrust forces. Radiation pressure from the Sun, even at interstellar distances, exerts detectable force on large solar panels or reflective surfaces. The spacecraft itself creates thermal gradients that induce subtle forces. None of these effects are large, but over decades they accumulate into significant velocity changes that must be accounted for in navigation calculations. Course corrections require propulsion systems that can fire precisely. A thruster, intended to adjust velocity by 1 meter per second, must deliver exactly that, not 0.99 or 1.01 meters per second. But thrusters have finite precision. Propellant flow rates vary slightly. Combustion efficiency changes with temperature and pressure. Even the most carefully calibrated thruster exhibits performance variations of 1 or 2%. Over many course corrections, these errors compound unpredictably. The spacecraft's mass changes during the mission as propellant is expended, complicating thrust calculations. Every kilogram of propellant burned alters the mass ratio, changing how much velocity change results from a given thruster firing. Precise navigation requires tracking propellant consumption with high accuracy, but measuring liquid quantities in zero gravity is surprisingly difficult. Propellant sloshes in tanks. Surface tension effects cause unpredictable distribution. Estimating remaining propellant to better than a few % accuracy requires sophisticated sensors and careful modeling. Relativistic effects further complicate navigation at high velocities. Special relativity predicts that space and time measurements depend on the reference frame. From Earth's perspective, the spacecraft has a certain position and velocity, but from the spacecraft's perspective, distances are contracted and time runs at a different rate. These effects, though small at 10% light speed, become significant when compounded over decades and light years. Navigation calculations must account for relativity consistently across reference frames. Gravitational perturbations from distant stars subtly alter the spacecraft trajectory. Even stars light years away exert tiny gravitational forces. Over decades, these forces accumulate into measurable velocity changes. The problem is that the masses and positions of many nearby stars are not known precisely. Stellar mass can be estimated from luminosity and spectral type, but uncertainties of 10 to 20% are typical. These uncertainties translate directly into navigation uncertainties for trajectories spanning light years. Interstellar dust and gas exert drag on the spacecraft, gradually slowing it. The magnitude of this drag depends on interstellar medium density along the trajectory, but that density varies and cannot be measured in advance. The spacecraft experiences slightly more drag passing through dense molecular clouds and less drag in a tenuous hot medium. These variations accumulate into unpredictable trajectory perturbations over decades-long journeys. Even assuming perfect navigation systems and propulsion, quantum mechanics imposes ultimate limits. The Heisenberg uncertainty principle limits how precisely position and velocity can simultaneously be known. The product of position uncertainty and momentum uncertainty must exceed Planck's constant divided by 4 pi. For a spacecraft massing thousands of kilograms, this quantum limit is negligibly small, but it exists. At some level of precision, quantum uncertainty prevents further improvement in navigation accuracy. The deceleration dilemma. Accelerating to 10% of light speed is difficult. Decelerating from 10% of light speed is equally difficult and far more constraining. This asymmetry creates perhaps the most underappreciated obstacle to interstellar missions, the deceleration problem. A spacecraft that cannot slow down cannot stop. It becomes an eternal wanderer, destined to hurtle past its target at tens of thousands of kilometers per second, glimpsing its destination for mere hours before plunging back into the interstellar void. The physics is unforgiving. Deceleration requires the same energy as acceleration. If reaching 10% light speed consumes energy equivalent to hundreds of nuclear weapons, returning to rest requires consuming that energy again. The rocket equation applies symmetrically. Fuel needed for deceleration must be carried during acceleration, increasing the total mass that must be accelerated, which requires more acceleration fuel, which adds more mass. This recursive problem effectively doubles the mission's energy requirements at minimum. Consider a spacecraft using nuclear pulse propulsion, Project Orion's concept of detonating nuclear bombs for thrust. To accelerate a 1,000-ton spacecraft to 10% light speed requires approximately 3,000 nuclear devices, each yielding 1 megaton. The spacecraft's mass at departure would be roughly 95% nuclear weapons. Now add deceleration capability. You need another 3,000 devices for slowing down. But these deceleration bombs must be accelerated to cruising speed along with everything else, increasing the initial mass substantially. The mathematics becomes punishing. With a mass ratio of 20:1 achievable, with high-performance nuclear pulse propulsion, you can accelerate to 10% light speed or decelerate from it, but not both. To do both requires staging, carrying deceleration fuel plus a deceleration stage, then accelerating this entire assembly. The compound mass ratio becomes 20 times 20, or 400:1. For every kilogram of payload arriving at Alpha Centauri, you must launch 400 kilograms from Earth. Alternative deceleration methods fare no better. Magnetic sails, enormous loops of superconducting wire, generating magnetic fields could theoretically break against the destination star's stellar wind. But stellar wind density drops with the square of distance from the star. Effective braking requires approaching within a few astronomical units, meaning the spacecraft must be aimed precisely at the star itself. Missing by even modest margins leaves the sail in regions where wind density is too low for meaningful deceleration. Laser-pushed light sails, like those proposed for breakthrough Starshot, face an even starker problem. The laser system remains at Earth. Once the spacecraft leaves the solar system, the laser can no longer push it. There is no way to reverse the thrust direction for deceleration. Some proposals suggest building a second laser system at Alpha Centauri to slow incoming probes, but this requires sending infrastructure ahead, which itself needs deceleration capability. The circular dependency is impossible to resolve. Gravitational assists might help. Approaching Alpha Centauri A or B on carefully calculated trajectories could steal orbital energy, slowing the spacecraft. But gravitational assists require precise approach angles and specific orbital geometries. The spacecraft must arrive at exactly the right position at exactly the right time relative to stellar positions that change over decades. Navigation errors of tiny fractions of a degree, unavoidable given the precision limits discussed earlier, would cause the spacecraft to miss the required trajectory and sail past without meaningful deceleration. Even if the spacecraft achieves a gravitational capture, it ends up in a highly elliptical orbit with aphelion extending many astronomical units from the stars. Circularizing this orbit requires additional propulsion to raise the perihelion, more fuel, more mass, more energy. The cumulative delta-V budget for deceleration, capture, and orbit circularization can easily exceed the original acceleration budget. Some concepts propose aerobraking using atmospheric drag against any planetary atmospheres to slow down. This works beautifully for missions within the solar system, where spacecraft approaching Mars or Venus can use atmospheric passes to shed velocity without expending propellant. But aerobraking requires knowing in advance that suitable planets exist with atmospheres of appropriate density. We have detected some planets around Alpha Centauri, but their atmospheric properties remain largely unknown. Banking $1 trillion mission on the assumption that a planet with the right atmosphere exists in the right orbit is gambling with catastrophically poor odds. Moreover, aerobraking at relativistic approach speeds becomes violent. A spacecraft entering an atmosphere at 10% light speed encounters air molecules with closing velocities of 30,000 kilometers per second. Each collision releases enormous energy, heating the spacecraft to tens of thousands of degrees. No heat shield could survive. The spacecraft would vaporize instantly, creating a brilliant meteor that briefly illuminates the alien sky before scattering its atoms across the upper atmosphere. The deceleration problem eliminates entire classes of mission architectures. Fast, lightweight probes pushed by ground-based lasers cannot decelerate. They are purely flyby missions lasting hours. Nuclear pulse rockets might decelerate, but only by sacrificing so much mass to fuel that payload capability collapses to nearly nothing. Fusion rockets, if they could be built, still face mass ratio challenges that severely constrain practical missions. Every propulsion system, no matter how energetic, must obey conservation of momentum. Slowing down requires throwing reaction mass backward, and that reaction mass must be carried the entire distance. Proposals for multi-stage missions, where the deceleration stage separates and slows, while the flyby stage continues at speed, merely partition the problem. You still need to decelerate something, requiring the same energy and mass. And if the deceleration stage is intended to establish infrastructure for later missions, it must carry substantial payload, communication equipment, landing craft, scientific instruments, power systems. The mass requirements compound rapidly. Perhaps most frustrating is that deceleration cannot be avoided or postponed. You must decide at mission design whether to include deceleration capability. If you launch a flyby mission and later regret the choice, there is no remedy. The spacecraft races toward Alpha Centauri at 30,000 kilometers per second with no possibility of slowing. Radio commands from Earth take years to arrive and cannot change the spacecraft's fundamental momentum. The decision to forego deceleration is permanent and irreversible. The deceleration dilemma represents a perfect example of how interstellar missions suffer from compounding constraints. Each problem, energy, mass, navigation, communication, is individually daunting, but they interact with solutions to one problem, exacerbating others. Carrying deceleration fuel increases mass, requiring more acceleration energy, demanding better propulsion, adding complexity, raising costs, lengthening development time. Every attempt to solve the deceleration problem makes the overall mission more difficult until no feasible solution remains. The gravity well trap. Earth's gravity creates an invisible barrier that every interstellar mission must overcome before even attempting the journey to the stars. This barrier, called a gravity well, requires enormous energy to escape and fundamentally limits what we can launch into deep space. Understanding gravity wells reveals why building massive interstellar spacecraft on Earth and then launching them is physically impossible, leaving us trapped at the bottom of a deep pit we lack the energy to climb out of. Gravity wells are often visualized as depressions in a rubber sheet, with massive objects creating deep dimples. Objects in the well, like spacecraft on Earth's surface, must expend energy to climb up the sides. The depth of the well determines how much energy is required. Earth's gravity well is relatively shallow compared to gas giants like Jupiter, but it is still profound relative to human energy resources and technological capabilities. The escape velocity from Earth's surface is 11.2 kilometers per second. Any object that reaches this velocity can escape Earth's gravitational pull entirely, coasting to infinite distance with no additional thrust. Chemical rockets achieve escape velocity by burning enormous quantities of propellant. The Space Shuttle system, including its external tank and solid rocket boosters, massed roughly 2,000 tons at liftoff, but delivered only 110 tons to low Earth orbit, a mass ratio of nearly 20 to 1. And that merely reaches orbit, not escape velocity. Reaching escape velocity from low Earth orbit requires an additional 3.2 kilometers per second of velocity change. This seems modest compared to the 7.8 kilometers per second already needed to achieve orbit. But the rocket equation makes every additional kilometer per second exponentially more expensive in propellant mass. A spacecraft in low Earth orbit must burn substantial additional fuel to break free of Earth entirely, and this fuel must first be lifted to orbit, requiring more fuel in a recursive spiral. Now consider the requirements for an interstellar mission. The spacecraft must not merely escape Earth, but accelerate to tens of thousands of kilometers per second relative to the Sunday. Earth's orbital velocity around the Sun is 30 kilometers per second. Escape velocity from the solar system at Earth's orbital distance is 42 kilometers per second. To reach 10% light speed, 30,000 kilometers per second, the spacecraft must achieve a final velocity 700 times greater than Earth's escape velocity. Chemical rockets cannot do this. The rocket equation, with chemical propulsion exhaust velocities of 4.5 kilometers per second, requires mass ratios exceeding anything physically possible for such velocity changes. Even nuclear propulsion faces extreme mass ratio requirements that make launching complete spacecraft from Earth impossible. The spacecraft mass at departure would exceed millions of tons for any useful payload, and no launch system can lift such masses against Earth's gravity. One proposed solution is orbital assembly. Launch components separately, assemble them in orbit where gravity is negligible, then depart from orbit rather than from Earth's surface. This avoids repeatedly lifting the entire spacecraft mass against gravity. But orbital assembly introduces new challenges. Spacecraft must be designed for modular construction. Components must survive launch stresses and space environment during storage. Robotic or human crews must perform complex assembly operations, and the assembly infrastructure itself must be launched and maintained. The International Space Station required more than 40 launches over 13 years to assemble, and it masses only 420 tons, a tiny fraction of what an interstellar spacecraft would require. Assembling a spacecraft massing thousands or tens of thousands of tons would require hundreds or thousands of launches, costing trillions of dollars at current launch prices. Every component must be lifted from Earth's surface, fighting gravity every meter of the way. Launch costs might decrease with reusable rockets and economies of scale, but gravity imposes absolute minimum energy requirements. Lifting 1 kilogram to low Earth orbit requires approximately 33 megajoules, that is, physics, not economics. At typical electricity prices of 10 cents per kilowatt hour, this translates to about $1 per kilogram in energy costs alone. Real launch systems must also pay for hardware, operations, maintenance, and overhead, keeping costs far above theoretical minimums. Some proposals suggest mining materials from asteroids or the Moon to avoid lifting mass from Earth. The Moon's gravity well is much shallower. Escape velocity is only 2.4 kilometers per second. Asteroids have negligible gravity. Raw materials extracted in space could be processed into spacecraft components without fighting Earth's gravity. But this requires establishing mining operations, processing facilities, and manufacturing capabilities in space, a multi-trillion-dollar infrastructure that must itself be launched from Earth initially. The lead time for such infrastructure is measured in decades. We must first develop the technology, then launch equipment, then establish operations, then begin production, then finally start building interstellar spacecraft. By the time this infrastructure is mature enough to construct an interstellar mission, half a century might have passed. And throughout this period, we continue paying to maintain orbital facilities, replace failing components, and support human crews if assembly requires human presence. Gravity wells exist at every scale. Leaving Earth's gravity well leads to the Sun's deeper gravity well. The solar system escape velocity at Earth's orbital distance is 42 kilometers per second. Achieving the tens of thousands of kilometers per second needed for interstellar travel requires climbing far up the Sun's gravity well, an energy expenditure that dwarfs the cost of merely escaping Earth. The Sun's gravity well extends effectively to infinity, gradually weakening but never disappearing entirely. Even reaching Alpha Centauri places you in its gravity well. If the mission requires entering orbit around one of the Alpha Centauri stars, or descending to a planetary surface, you must then climb down into new gravity wells and potentially back out again. Every gravity well interaction requires energy either for propulsion to brake against gravity or for propulsion to escape afterward. The cumulative energy budget across multiple gravity well transitions becomes staggering. Gravity assists can help extract energy from planetary motions, but they only work if planets happen to be positioned correctly when the spacecraft arrives. For interstellar missions, journey times are decades, and predicting planetary positions decades in advance requires knowing orbital parameters with extraordinary precision. Small errors in assumed orbital periods accumulate into large position errors over decades, making gravity assist trajectories unreliable for interstellar distances. The gravity well trap is not merely about launch costs or assembly logistics. It represents a fundamental energy barrier. Every kilogram of mass launched from Earth must be given sufficient kinetic energy to escape. That energy must come from somewhere, either chemical propellant, nuclear reactions, or some other source. The total energy required grows with the spacecraft's mass and with the depth of the gravity well being escaped. For interstellar missions requiring thousands of tons to be accelerated to extreme velocities, the energy requirements exceed anything human civilization can provide. This creates a paradox. The spacecraft must be massive to carry sufficient fuel, shielding, redundancy, and payload for multi-decade journeys. But massive spacecraft require enormous energy to launch. That energy must be generated on Earth and somehow transferred to the spacecraft. No power source we possess can generate the required energy efficiently enough to make the mission feasible. Nuclear weapons contain sufficient energy density, but assembling thousands of nuclear devices in orbit violates every non-proliferation treaty and creates catastrophic risks of accidental detonation during assembly or launch failures. The information decay problem. Information degrades over time. This fundamental principle of thermodynamics applies as ruthlessly to spacecraft data as to any other system. For interstellar missions lasting decades, information decay becomes an existential threat. The knowledge required to operate the spacecraft, interpret its findings, and complete the mission slowly degrades through multiple mechanisms until the mission objectives become unachievable, even if the hardware somehow survives. Begin with data storage media. Every information storage technology has finite longevity. Magnetic hard drives develop bit rot, random flipping of bits due to thermal fluctuations, magnetic field decay, and cosmic ray strikes. Error rates of 1 bit per terabyte per year sound negligible, but over 40 years, these errors accumulate into substantial data corruption. Error-correcting codes can detect and fix some corruptions, but error correction has limits. Once error rates exceed the correction capability, typically when more than a few % of data is corrupted, information becomes unrecoverable. Flash memory used in solid-state drives degrades through write-cycle exhaustion. Each memory cell can be written and erased only a finite number of times, typically 10,000 to 100,000 cycles for modern flash. During a multi-decade mission, continuous data recording and erasure to reuse storage capacity eventually wears out memory cells. The drive fails not catastrophically but gradually, with increasing numbers of bad blocks that must be avoided. Storage capacity shrinks over time until insufficient space remains for critical data. Optical media like CDs and DVDs degrade from radiation exposure and thermal cycling. The dye layers that encode information gradually deteriorate, causing increasing read errors. Redundant copies help, but all copies suffer similar degradation rates, eventually rendering data unreadable. Even supposedly archival-grade optical media rated for decades show accelerated aging in space environments that manufacturers never tested for. Radiation causes single-event upsets in memory random bit flips from cosmic ray strikes. For a terabyte of data, assuming a cosmic ray flux of 1 particle per square centimeter per second and a sensitive cross-section of 1 square micrometer per memory bit, upset rates approach 1 bit flip per minute. Over 40 years, every bit in storage will be flipped multiple times unless continuously error-checked and corrected. This requires constant processing power to scan memory, detect corruptions, and restore correct values from redundant copies or error-correcting codes. But error correction itself requires information parity, bits, checksums, redundancy. This overhead typically doubles or triples storage requirements. A spacecraft designed to carry 1 terabyte of science data actually needs 2 or 3 terabytes of storage capacity to accommodate error correction. And the error correction codes themselves can be corrupted by radiation, creating a recursive problem where the redundancy meant to protect data becomes unreliable. Software represents a special category of information vulnerable to decay. The flight software, millions of lines of code controlling spacecraft operations, resides in memory that suffers the same radiation damage as data storage. A single bit flip in program code can have catastrophic consequences, jumping to wrong instruction addresses, corrupting control logic, crashing systems. Radiation-hardened memory and error correction mitigate these risks, but cannot eliminate them entirely. Worse, software contains latent bugs errors in logic that exist from the moment the code was written, but only manifest under specific conditions. These bugs might lie dormant for years until some rare combination of events triggers them. When a critical bug activates during the mission, perhaps after 30 years of flawless operation, there is no possibility of uploading a software patch. Earth is years away by radio signal time. The spacecraft must handle the failure using only its onboard capabilities, potentially without the software functionality needed to diagnose or work around the problem. Configuration data poses additional decay risks. The spacecraft stores calibration parameters for instruments, offset corrections, sensitivity factors, timing constants. These parameters were carefully measured during ground testing and are essential for interpreting science data accurately. But the hardware changes over decades of operation. Sensors drift, optics degrade. Timing circuits shift frequency. The stored calibration parameters gradually become inaccurate, causing increasing errors in measurements until science data becomes unreliable or meaningless. Ideally, the spacecraft would periodically recalibrate itself using observations of known targets, standard stars for optical instruments, known radio sources for receivers, internal reference targets for other sensors. But recalibration requires knowing which targets to observe and what their properties should be. This knowledge exists in databases stored in spacecraft memory, which themselves suffer information decay from radiation and media degradation. If calibration databases become corrupted, the spacecraft might recalibrate incorrectly, making instruments less accurate rather than more. Human knowledge decay operates on different timescales, but is equally inevitable. The engineers who designed and built the spacecraft will age, retire, or die during a 40-year mission. Their expertise, deep understanding of how systems work, knowledge of undocumented quirks and workarounds, intuition about likely failure modes, cannot be fully transferred to replacement personnel. Documentation helps, but documentation is always incomplete. Subtle details that seemed obvious during design become mysterious years later when different people try to interpret telemetry from malfunctioning systems. Institutional knowledge degrades as organizations change. The space agency managing the mission will undergo restructuring, budget cuts, leadership changes, and shifts in priorities over 4 decades. Each reorganization disrupts continuity, personnel transfer to other projects, budgets for ground operations decline as initial enthusiasm fades and newer missions compete for resources. The institutional capacity to support the mission erodes gradually until minimal staffing remains perhaps too few people with too little expertise to respond effectively when critical problems arise. Even the mission's scientific objectives decay informationally. The spacecraft was designed to answer specific questions considered important when the mission was approved. But scientific priorities change. 40 years of astronomical observations from Earth-based telescopes might answer the mission's original questions before the spacecraft even arrives, making its data redundant. Or scientific consensus might shift, rendering the planned measurements obsolete or misdirected. The spacecraft continues gathering data that no longer addresses questions anyone cares about. Language and terminology drift over decades. The documentation written when the spacecraft was built uses technical terms and acronyms common at the time. 40 years later, these terms might be obsolete, replaced by new terminology. Future mission controllers might struggle to interpret technical manuals and troubleshooting guides written in what amounts to a technical dialect they never learned. The information remains physically present but becomes linguistically obscure. Data transmission across light years introduces its own information decay. As discussed earlier, signal strength attenuates with distance squared. Weak signals require extensive error correction to ensure accurate reception, reducing effective data rates. But error correction can only compensate for so much noise. Eventually, signal-to-noise ratios drop below levels where reliable communication is possible. The spacecraft might still be transmitting, but Earth receivers cannot extract meaningful data from the noise. Information decays in transit, arriving as unintelligible static.